Welcome everybody to the Phosphorus session this morning. So to everybody here and to those joining virtually as well. I'm Paul Lavender, Water Utilities Director for Royal Haskoning DHV. I'll be chairing this session through to the lunchtime break. So in terms of questions, if people want to put their hands up to ask questions, or you could submit them through the Hopin platform, same as in the last session. And yeah, for those virtually as well, you can just submit through Hopin. I'll be picking them up here to ask the speakers. So without further ado, we'll go to the first talk, which is Peter Eddowes of Arvia Technology. He's going to be talking about process integration for a circular economy of phosphate.
Good morning, everyone. Thanks, Paul, for the introduction. And thanks for the opportunity to get me to talk about my work. This is my first EWWM conference, so I'm quite new to wastewater management. I'm an electrochemist, and I'll be talking about my work at Arvia, integrating two electrochemical processes for the recovery and reuse of phosphate. So I'll first go through the basic questions, then go on to talk a little bit about Arvia, and then discuss the experimental results. So what have we done? We've done a 3-month Innovate UK funded project as a proof of principle for the phosphate recovery. This showed some good results, and we've just filed a patent for the process. The first electrochemical process uses Arvia's NIAX system to remove organic pollutants, and this then goes on to electrocoagulation to remove phosphate, a clean phosphate solid which can be reused as fertilizer. So why remove phosphate? I think everyone knows that it's responsible for eutrophication of surface waters. Currently, Mr. Bickers uses ferric dosing to get rid of phosphate, to add in chemical coagulants to water. Electrocoagulation is just in situ production of that coagulant. Yes, it does remove phosphate, but you produce a toxic sludge. With the organics, it's still in solution. Biological processes remove phosphate as well, but again, some of the organics persist. Other processes will remove organics, but not phosphate. So ozone is good at destroying pollutants, but it's expensive. And GAC removes organics, but again leaves a toxic sludge. We think Arvia's, so this is a new process, so I'm going to call it Arvia's Pure Recovery because that's the only name we've got for it at the moment. This solves both those problems. So this is aimed at utility companies who need to remove phosphates from their effluents. And these consent limits are falling all the time. And regulations are coming soon to force utility companies to remove priority substances, so organic pollutants. We think RV's peer recovery can solve this problem. So how have we done it? On the left there, we've got a neutral wastewater containing phosphates and organics. This goes through our NIAX process to destroy the organics. It also electrolyzes water into equal quantities of acid and alkali. So the acidic effluent then goes on for the electrocoagulation process, then to a settlement tank where the pH is adjusted by the alkaline stream of the NIAX process. And this drops out a clean phosphate solid and a clean neutral effluent. So who is Arvia? We're a company of 35 staff in the Heath at Runcorn. We have projects in China, Chile, New Zealand, Austria and Spain, so few. And our main business is the NIAX process to destroy nuisance organics like herbicides, pesticides, pharmaceutical intermediates and such. So NIAX is an absorbent, so it will absorb pollutants. It's also electrically conductive. So when you pass a current through it, you mineralize the organics into carbon dioxide and water. This frees up the NIAX to absorb further pollutants, and so it's regenerated in the process. On to our experiments. So I'm starting from scratch with these experiments. So beaker cells, then moving on to flow cells at the 50 litre scale. And I'm treating water spiked with phosphate, comparing neutral electrocoagulation with a acidic electrocoagulation, so comparing like for like. It's a bit difficult to treat with organics because there's so many different organic compounds that you wouldn't know what to spike it with. So we've got a real-world sample from United Utilities Longton wastewater treatment plant, and I'll show you the results of that later. So the graph on the left is showing percent phosphate removal against power consumption. The red dotted line is electrocoagulation under neutral conditions. And you can see there it's struggling to remove all the phosphate because the conditions aren't right. The flow regime is probably not right in that beaker cell. An iron dissolution is struggling to diffuse into the solution to remove the phosphate. However, when you do that under acidic conditions, like in after the NIAX process, there's no problem removing the phosphate down to very low levels, 0.12 ppm there. And of course, there's lower power consumption in doing that as well. So this is a well-known problem with electrocoagulation, is the electrodes can foul. You get nasty deposits on there, and this consumes energy in the process as well. And there's no doubt a few of you here that have put a lot of effort into solving this problem. As well, because you get precipitation in the electrocoagulation cell, the gas-created electrodes can make some of the precipitate float, some of it sinks. And so you need a tertiary solid removal to get rid of that solid. So when you do electrocoagulation on acidic effluent, like in after the NIAX process, the electrodes stay nice and clean, and the effluent in the electrocoagulation cell, there's no precipitate, and that stays nice and clean as well. You then go on to a settlement tank where you add alkali from the alkaline stream of the NIAX process, and there you get a nice bright orange clean phosphate precipitate that just settles at the bottom of the tank. Then on to once through flow cell, treating 50 litres at a time. So the conditions, the main condition to look out for is the flow rate. So high flow rate, there's less iron dissolution, less phosphate removal. Low flow rate, more iron dissolution, and you remove more phosphate. So if you get the flow rate right, you've reduced the phosphate down to 0.03 ppm there, and also the iron levels are really quite low as well. So the table there is showing the bottom two lines are showing the RVA phosphate removal at two different flow rates. And you can see there, as you increase the flow rate, the phosphate's gone up from 0.03 to 0.26, but the power consumption's gone down. The top line showing neutral electric coagulation, which is a higher power consumption and also a lower current density. So you want higher current density because this means you've got a smaller plant for the same throughput of effluent. So you're reducing your capex costs, and of course the lower power consumption reduces your operating costs as well. We then looked at other flow cell designs from that reference there. So what we have here is a flow cell with effluent coming in from the left, going through a serpentine path through electrodes, and exiting at the right. We've got the two outer electrodes are connected to the power supply, and two inner ones are bipolar, standalone electrodes. Again, you can see that we've got a higher current density for the obvious phosphate recovery. Again, the neutral conditions, it was difficult to remove all the phosphate, but if you reduce the flow rate there and increase the power consumption, you'd also get a lower power consumption for the phosphate recovery. In this setup, the actual power consumption was 3 times that of the previous cell, but electric coagulation in acidic conditions still work quite well. Now on to the Longton final effluent, which you can see on the left bottle there. It's got some colour from the organic contaminant. And the bottle on the right is showing you after the NITX process, it's removed all the colour. So the incoming effluent has got 23 ppm phosphate and a COD of 57. We removed all the phosphate down to 0.06 ppm, kept the iron levels low, didn't quite remove all the COD, but as you can see from the COD to TOC ratio, we've oxidised that organic, so the original contaminant does not remain, and it's more likely to be oxidised into organic acid. Compare that with the last column there, electric coagulation in neutral conditions. Haven't quite removed as much phosphate, there's still some iron there. It did a good job at removing the COD, but from the ratio of COD to TOC, you can see it still contains the original contaminant. And also it took more power to remove that contaminant. Again, the current density for the obvious pure recovery is much higher, meaning a smaller plant for the same throughput. So this is the treatment of the Longton effluent. First, on the left is showing you after the NITX process and after iron oxygen dissolution. So you've got a clean solution, no deposits. You then go through a settlement tank to adjust the pH with the NITX process alkaline stream, and you get a nice bright orange precipitate of iron phosphate. It just settles at the bottom of the tank. Compare that with neutral electric coagulation. We've got a brown-green precipitate, which contains the original organic contaminant. Some of the precipitate's floating because of the gas bubbles generated in the cell, and some of it's sinking as well. So you need some tertiary solid removal to treat that solution. So just to summarise, the benefits of obvious pure recovery, we're producing a clean solid for selling on as a crop nutrient. Electrocoagulation produces a more toxic voluminous sludge, and that's got costs associated with its disposal. For just phosphate recovery alone, it's got a 5 to 10% lower power consumption, but this increases with an increase in COD. The saving increases, sorry. There's no electrofouling in this process, and the precipitate can remove by settlement tank, whereas normal electrocoagulation removes tertiary solids removal. No chemicals are required from these two processes. The pH adjustment's done internally from the two processes, whereas the final effluent from electrocoagulation is high, so you need some adjustment to get it back down to neutral. It works for a wide range of cell designs and operating conditions, whereas for electrocoagulation you need specific conditions, otherwise you get electrofouling. We actually dissolve less iron per content of phosphate, so the electrodes will last longer as well in this process. And phosphate's a limited resource, and so recovering and using the phosphate is a benefit for everyone really. And farmers nowadays are looking to reduce their carbon footprint. And at the moment in the UK, all farmers import phosphate, and this phosphate's mined. So they think they'd welcome a local source of phosphate. And this could become a revenue for water companies as well. So what next? So we'd like to scale up the process to a pilot study and get some good data for 18 months, fine-tune the process, but we'll need some funding to do this. So we're possibly looking for the Off-Hot Water Challenge to get funding to look at situating a pilot study at a designated demonstrator facility or a small wastewater treatment plant. And there's a typical design of our units. The NIX process usually goes in a 30-foot container, and there we've put both processes in a 30-foot container to be situated at one of those locations. We'd also welcome some collaborations from Europe, if there's any funding from perhaps the Green Deal initiative as well. So that's the end of my presentation. There's my contact details if you want to get in touch, and any questions. Thank you.
Hello. Okay. Thank you for your talk. I think it's particularly timely with so many phosphorus consents going in and the recent pressures we've seen in the press around ferric supply. So I've got one question here from Chris Thornton. He's asking, how acidic is acidic? It says, what pH is that at the exit of the NIX process?
We found that the more acidic you can get it, the better the benefits for electrocoagulation. So we're talking about pH of about 3, but you still see some benefits at about pH 4.
And I was just wondering, in terms of the precipitation of phosphorus, it says that's from the alkaline stream. Is that what precipitates is calcium phosphate?
It's mainly iron phosphate, but there will be some calcium transferred into that alkaline stream as well, so there will be some calcium present.
Sure, okay. Is there any other questions? There's one at the back.
Hi, Paul Picard, Aquinviro. I followed the process, but it seems to kind of skip over what the NIX process actually does. I see it generates the acidic and alkaline streams. How does it actually do that?
So what was the question? How did it do that?
Yeah, I mean, what was the NIX process?
So it's an advanced electrochemical oxidation process. So this process is carrying the anode, the positive electrode, Typically, in an electrochemical cell, you've got an anode and cathode. At the anode, you would oxidize water to protons to make acid conditions, and the cathode will become alkaline. As you make oxygen and protons at the anode, you produce highly reactive hydroxyl radicals, and it's these radicals that actually destroy the organic.
Yep. Fran, a question at front.
Thank you. I'm Matthijs Oosterhuis, Royal Haskoning DHV. I was wondering, do you expect you can combine your technology with normal activated sludge systems, or do you propose a completely new system? In Holland is the normal technology conventional activated sludge. And if you want to treat your wastewater in a physical, chemical way, you need to renovate the whole system. How do you think about it?
So this is a tertiary treatment that can be added on to the end of the normal processes.
It's a post-treatment technology?
That's the way I see it at the moment. I mean, I'm quite new to wastewater, so I'm not entirely sure of all the processes, but that's where I see it at the moment. Whether it can fit in somewhere else, we'd also look into that as well. But it'd have difficulty treating suspended solids, especially in the NIX process. So after all
if
those
there's more
have been
contaminants there, the efficiency would drop significantly, I'd imagine, wouldn't
Sorry,
it?
say again?
I guess if it's earlier in the process stream, so there's more contaminants, and the efficiency would be affected.
I think it's more to do with any solids that are present. That they might affect the cells, electrochemical cells. The higher the contamination, usually the higher the efficiency in these processes. So there is room for consideration in other parts of the treatment.
Okay. I've got a couple more questions coming in here. One from Rowan Huggins saying, can you explain further how the NIX process works in terms of how it creates the two different effluent streams?
Okay, so this is a divided electrochemical cell. So there is a membrane in there. As I explained before, the anode will create acid conditions and destroy the organic. Cations from the effluent will then pass through the membrane to provide the electrical current circuit, and you get a reduction of water into hydrogen and alkali in the cathode stream. I think that explained it.
Yeah. And just another question here, just a more general question around whether you see a market for the recovered phosphorus in the UK. Do you think that's something that you'd be able to potentially market?
I think there will be, as I said before, from the farmers looking at their carbon footprint. They'd welcome a local source of phosphate. Agreed, it may not be a huge amount per tonne, but it's a limited resource, yeah. And we're recovering it and reusing it, which is always be a good thing.
Okay, is there any other questions? A couple at the back.
Hi, Tim Holloway, University of Portsmouth. I was just going to ask about whether you've got a feel for the amount of CO2 that's released as a result of it.
It's dependent upon the organic contaminants there. Sometimes, as in that, the long-term effluent is not complete, and you end up with organic acids, which can be treated in other ways. I haven't done a calculation to measure the exact amount from a certain throughput, but it will be dependent upon the organics that are present.
Okay. I think there's another couple of questions over there.
Hi, Ahmed from Colina. Pete, in your comparison of your AVIA system against electrocoagulation, did you apply the same amount of current?
No, I applied the same voltage and measured the current. This is why I saw different higher current densities in the acidic solution, because essentially it's more conductive and you can pass more current through it. And as I said before, you need a higher current density for electrochemical processes because this reduces the size of plant for the same throughput of solution and reduces your capex cost.
Sorry, last one. In your schematic, you showed a process that involved the adsorption and oxidation.
Yeah.
Was this process similar as well? Did it involve some stage of adsorption process?
Sorry, can you repeat that?
In your schematic, when you showed the AVIA process,
Yeah.
it had an adsorption stage where you had a NIX system.
Yes. So yeah, there's an absorption onto the NIX absorbent, yes,
So,
in the first process.
So the data you presented, was it post-adsorption, or is that there is a breakthrough first and then you apply the current?
Yes, you can operate like that. You can just wait until the organic is all completely absorbed on the absorbent and then apply current. But it's a regenerative process, so there's actually no need to do that really, as the flow rate will bring the organic to the absorbent surface, and it does that continuously.
Thank you.
Okay, so I'm conscious of time. We'll just need to move on. But yeah, thanks again, Peter, for that presentation, and good luck with the piloting. And hopefully you better come back and present the results of that next year. So thank you.
Thank you very much.
Okay, so our next speaker is Ben Hazard from T-Tech Process Solutions. And Ben is going to be talking about the modular T-Tech solution, satisfying growth drivers for nitrogen and BIOP removal in a single treatment step. Thanks, Ben.
Thank you, Paul. Good morning, all, and welcome. So as Paul said, I'm going to be talking about the work that we've been doing in developing a modular version of a pre-existing process called the T-Site process, and looking at how it incorporates biological phosphorus removal, as well as how it satisfies a number of other drivers such as growth and total nitrogen removal and stuff like that. First, a very brief company overview. So T-Tech Process Solutions is a recently established company with a focus on delivering conventional and perhaps more advanced water and wastewater treatment technologies, as well as providing MCCs, control panels and systems integration. And we also have a off-site manufacturing assembly facility in our workshop in Southampton. And one of the things we're keen to do at T-Tech is to sort of form close relationships with process specialists so that we can sort of seamlessly integrate their technologies into our process solutions. So the key one here today is our partnership with SFC Umwelttechnik, and it is with them who we are developing the T-Site process with. So I won't go into this slide too much, but these are just sort of the different areas that we work in. We do have a stand in the exhibition hall, so please do come and say hello if you want to find out more about what we get up to. Okay, so today there's two key messages I want to sort of get across. One is around sort of describing the modular T-Site process and how it incorporates BIOP removal, and sort of how this compares to what appears to us as the default option for P removal, particularly for the smaller sites, which just seems to be chemical dosing plus tertiary treatment. And the second point is around sort of proposing a more holistic view to water treatment upgrades. So for sites that have multiple drivers, instead of sort of picking a solution to each one individually, can we look at providing one solution that meets all of these drivers in one? So that's really where the benefits of the T-Site process become apparent, because it can satisfy multiple drivers in a single treatment step. So here's the process description. So it is a type of cyclic activated sludge process, which is fundamentally based off the traditional sequencing batch reactor, which I'm sure a lot of you will be familiar with. So always more than 2 tanks in parallel that run on a batch cycle, and their phases are out of sync with each other. So you can see in the bottom left here sort of the cycle timings. Rather straightforward. There's 2 hours of filling and aeration occurring at the same time, followed by an hour of settlement where everything is switched off and the biomass that you've accumulated settles as a sludge blanket and falls towards the base of the tank. And then finally an hour of decanting where around the top third of clear treated effluent is drawn off from the surface of the water via the decanter. And then that continues round on a cycle. So as you can see, if you have 2 tanks, you will always have continuous influent, therefore there's no buffer tank required. And with 4 tanks or more, you'll have a continuous decant as well, which can be important for sites where perhaps you need disinfection or something on the back end. So of course the size of the tank and the number of basins or cells can be adapted depending on what the needs of the site are. In terms of equipment and moving parts, again, it's reasonably straightforward. There's an inlet line which goes through a motorized valve or a penstock, which is used to sort of direct the flow to whichever tank is being filled. Flow then passes through an anaerobic selector zone, which is very important to the sort of the process design, but in terms of construction, it's rather straightforward. It's just a series of baffle walls which generate a plug flow path. Although it's anaerobic, there are coarse bubble diffusers at the base of each chamber of the selector zone, and this is for in periods of low flow you may need to apply a bit of air to sort of create some disturbance for any solids that may have settled. But this only occurs for around 5 minutes, approximately once a day, to maintain those anaerobic conditions. So from here it passes into the main aeration zone, which on the base there is an array of fine bubble diffusers, which are supplied by an arrangement of air blowers. And also submerged within the tank are RAS and SAS pumps. So the RAS pump continuously returns a portion of the mixed liquor from the aeration zone back into the first chamber of the selector zone. And this is occurring only in the fill aerate stage. There's also a SAS pump which draws off a portion of the sludge towards the end of the decant phase to maintain a certain mixed liquor within the tank. Again, the decanter, so this is a variable speed motor-driven decanter used to draw off the clear treated effluent, and because it's motor-driven, you get a nice controlled rate of decanting, so the decanting will last the whole hour. So as I said, the most important part really in the design of the process is the design of this selector zone and the internal recycle as well through the RAS pump, and particularly important for the enhanced biological removal portion of the process. So with those 2 features combined, what we're trying to do is create the perfect conditions for the growth of phosphorus accumulating organisms, or PAOs, which then biologically accumulate phosphorus in the liquid within them, and then these are withdrawn during sludge wastage. So with that in mind, results we see typically for existing sites, less than 1 milligram per litre total phosphorus with purely biological removal, and then if you need to get even lower, which is fairly common, we can get to around 0.3 milligrams per litre with top-up chemical dosing. And this is primarily due to the good performance in terms of solids removal for the process, because obviously once the biomass has taken up the phosphorus or it's been precipitated out with the chemical, you then need to remove it effectively from the treated effluent. So that is how you get sort of overall effective phosphorus removal. So in the T-site process, we typically see less than 5 milligrams per litre without tertiary filtration. So that is quite key there. And of course, every site is different. It has to be assessed on a case-by-case basis. But based on the sample results from previous installations, we believe this to be generally possible in most cases. Next 2 points are sort of around this more holistic approach. You know, the top is about phosphorus, but the rest is around achieving total nitrogen removal. So in the process, simultaneous nitrification and denitrification is possible, all within the aeration phase. And the last point is around the small overall footprint due to the lack of buffer tanks and potentially primary and also secondary treatment. And this is particularly useful for the more rural sites which we're targeting because of ease of operation and maintenance and things like that. Okay, so the TSAC process in general has been around for over 20 years, over 500 installations worldwide. But these are typically larger structures, concrete tanks, much larger throughputs. You can see some pictures on the left here. The one at the bottom, one in Malaysia, which has a PE of 1.2 million, so quite large. And what we want to do now at TTEC is take all of that learning from the historic previous installations and condense it down into a more modular solution. So this adds a number of benefits in that you can build and assemble the plant off-site and then ship it to site as one unit, minimizing the amount of time on site and all the health and safety risks associated with that. And on top of that, you only need to design sort of a few standard sizes, and then you can scale out depending on the needs of the site. And finally, it also sort of provides a bit of future-proofing. So if there is population growth or something in the future, you can just bolt on additional units. So this slide is all about sort of how it fits in the site and what it looks like, and how it compares to, you know, what, like I said before, what we see to be the default. So fairly typical treatment works here: inlet works, primary settlement tanks, trickling filter, and final settlement. So the default option, typically 2 or sometimes even 3 point ferric dosing. And sometimes if there is an ammonia consent, you will see alkalinity dosing as well, plus flock tanks and tertiary treatment. But with the TSAG option, you can install it as a side stream with or without PSTs, top up ferric dosing if necessary. And then what we've seen as well is often these sites, the existing assets are perhaps aged or not working as they originally were. So in most cases you can sort of remove or decommission what is there. So this is just a bit of a comparison between the existing units, the historic concrete structures and the modular solution. So Denrobek selector zone, normally formed with concrete baffles, but in the modular design we've opted for vertical pipes. That adds to the rigidity, and they're connected just with T-pieces, so you generate that flow path, and these could be constructed as one unit and even lowered in altogether. And you can see as well, in each one is the pipe that goes down to the coarse bubble diffuser at the bottom. Typically between 6 and 10 compartments or chambers, with a contact time greater than an hour. The decante slightly changed as well. So instead of an arm that is lowered down on a spindle, a penstock has been modified. So this lowers down vertically and the water wears over. Still has the floating scum guard to prevent any floating materials from entering into the treated effluent. So in terms of applications and the different sort of sizes we're looking at, we will still look at the much larger plants, but this will typically from design and provision of the individual components. And then next below that are the medium-sized plants. So this is 1,500 to 3,000 population equivalent, and these are constructed out of sectional stainless steel. So there will be some small construction on site, but this is typically much quicker than the concrete solutions. And then the ones that you saw in the render earlier are GRP tanks, and these can be assembled as one unit off-site, and we've sized them basically so that they can fit on the back of a lorry and taken in one piece. And as well, you can see other designs as well. They don't have to be circular tanks. The circular tanks provide the smallest footprint per volume, but there are sort of more containerized units as well that we've looked at. And also retrofit solutions as well. So many of the historic installations have been retrofitted into existing ASPs or SBR plants. So this slide just summarizes the sort of the various applications at which it would apply, various drivers, and as I said before, really the benefits become apparent when there's multiple of these drivers that you're trying to satisfy, really. So if there is BioP, and there's also a need for growth, and perhaps also tightened ammonia or total nitrogen consent coming in, that's where we're sort of targeting. So how do we achieve effective enhanced biological phosphorus removal? As I said before, sort of two elements are required. You need the conditions that favour the growth of PAOs as opposed to other bacteria. And then you also need to have effective solids removal to remove the solids or the biomass, the PAOs. So in the T-site process, this is formed right at the bottom there through the anaerobic selector zone. So on the next slide, I'll go through the BioP principle and why a cycle of anaerobic conditions and aerobic conditions are required to remove phosphorus biologically. But in terms of solids removal, there is the mechanically driven decanter. So as I said, this is a controlled operation for removing the treated effluent. So instead of it going down, if it goes down quickly, if it's a floating decanter, it might sort of start to disturb the sludge blanket that's formed towards the base of the tank. And also undisturbed settlement, so this is quite important. So in the overall cycle diagram, in that hour of settlement, there's nothing else going on. There's no fill, settle, decant, anything like that. The RAS pump is switched off, everything's switched off, so you get a nice sludge blanket being formed with no external turbulence. And the final point there is macroflux formation. So with the selector zone, it does what selector zones do, which is select for good, dense, flock-forming bacteria, as opposed to filamentous bacteria, which could potentially cause sludge bulking. And the size of these are sort of somewhere between normal activated sludge and granular. So they still settle nice and quickly and form a good blanket as well. So the principle of BioP, sort of very slimmed down diagram here of the internals of a PAO. So in the anaerobic selector zone, the organisms take in readily biodegradable COD in the form of volatile fatty acids and turn them into PHA storage products. So just imagine they're just taking in the VFAs, the food source. But to do this, they require a source of energy, so in the form of biological energy, ATP. And this is formed from their stored polyphosphate chains. And in doing that, they break a bond between the chains and orthophosphate, which is then released into the bulk of the fluid. So in fact, in the anaerobic zone, the liquid phosphorus concentration increases. Now in the aerobic zone, sort of the opposite happens. Oxygen is applied, and the PHA storage products provide both carbon for cell growth and energy again, and the bonds are reformed between the polyphosphate chains and the ortho-P, which is in the fluid. And because the cells have grown, they're able to uptake more phosphorus than they originally released, and you get a net sort of removal of phosphorus there. And this is known as luxury uptake. So for a project that's currently in construction, not with a modular solution, I must add, but in the UK at the minute, a site with a PE approximately 2,000, 0.3 milligram per litre annual average P consent. I did a sort of a desktop study on what the chemical consumption would be for T-site solution versus a conventional solution, 2.4 dosing, with alkalinity dosing in this case, and tertiary treatment. So because of the denitrification benefit of the T-site process, this means that your sodium hydroxide dosing was not required. And because of the BIOP removal capabilities, the ferric sulfate consumption was reduced by about half as well. So if you add all that up and sort of convert it into tanker loads, you can see that there's quite a large reduction there. So in terms of you're reducing chemical consumption and costs, but also carbon footprint in terms of tankerage as well. So on from the BIOP, just want to touch on this very briefly in terms of the simultaneous nitrification and denitrification. So as I said, the macroflocs are large compared to conventional, and they have the benefit that granular sludge has in that they're able to form sort of distinct a gradient of zones within them, where you have aerobic conditions on the outside of the flocks, and then towards the inside you have anoxic conditions. So the flock as a whole is able to perform nitrification, which is the conversion of ammonia to nitrite and then eventually onto nitrate. And this is with the inclusion of oxygen. And then in the center of the flock, where oxygen is not present, you get denitrification occurring, where nitrate is converted to nitrogen gas, which then bubbles off. So normally you would perhaps need an extra phase in your SBR cycle, an anoxic mix phase, for example, where you may need mechanical mixers and things like that. So in this example, that's not needed, which is, I guess, is another plus. Just a few references here now. I think these are quite interesting. So this is a site in Austria in the Alpine region. What's quite interesting about this site is sort of the opposite of seaside towns in the UK. Instead of everyone coming into the summer for their holidays, everyone goes here to go skiing. So in the winter, the population pretty much doubles from its summer population. So you've got that on top of the issue of the cold temperatures. So just on the graphs here, we can see, let's start with the phosphorus, which is in the middle there. Quite interesting at this site. So the consent currently is 1 milligram per litre. And you can see before the yellow dotted line, it was achieving this purely on a biological basis. But then they wanted just to see how low they could go. So after the yellow line, they switched on ferric dosing, and they were able to achieve, around the 0.3 milligram per litre mark. Again, that's without tertiary treatment. And this is closely linked to the solid state that you can see here, which is comfortably lower than 5 milligrams per litre. Another site here in Germany, quite a large site, this one, and the circular tanks you can see, it's quite interesting. The circular tanks are divided in two, and each semicircle is a individual basin. So quite an interesting construction for this one. But again, just looking at the phosphorus data, we can see that it is around the 0.5 mark there. 0.4. And finally, one in Czech Republic. So this has quite a high industrial influence. You can see this is evidenced by the quite noisy influent data. But looking at the effluent, you can see it's rather steady, particularly for the phosphorus. So it does spike in a few points, but generally around sort of the 0.5, maybe less. And again, with the solids, generally around 0.5 and lower. Okay, so just to summarize then, I think I've said this enough times, but what we want to propose is that the modular T-site solution is good for BIOP, but really the benefits come clear when there are multiple drivers on these sites, such as catchment growth, nitrogen removal. And maybe if the drivers aren't necessarily there currently, what's coming in the future, it's best to get everything done now instead of having to revisit sites time and time again. Okay, thank you for listening. Any questions?
Okay, great. Any questions for Ben? Yeah, over there.
Thanks for that. It was very interesting. Steve Palmer from Stantec. You were saying that you've got a carefully designed selector zone, which is giving you, in effect, what you're doing is selecting for more PAOs, you're selecting for more flock formers by the conditions you maintain in that zone. And it looks like, from what you're showing us, that you're getting slightly larger flocks as well, which would make sense because what you're doing is triggering some of the regulatory pathway that puts you towards more EPS production. You were saying that you get better than less than 100 on your SSVIs. With those flocks being a bit bigger, having probably more EPS in them, are they a bit denser? What's your upflow rate when you decant?
I'm not sure on that, to be fair. I do know that the sort of the general size, I believe, is around 0.4 millimeters in terms of sludge size. But yeah, I'm not sure on the value after. But I can get that for you if you want to grab us in the hole later.
Any more questions?
Hi, Caroline from Blue Water Bio. You're showing your modular design with vertical pipes for anaerobic selectors for the POA. So in the SBR operation, how the biomass in the vertical pipe get into the aerobic zone? Because you need the P uptake to remove the P.
Sure. So can I just go back? Yeah, so you can see, so the pipe on the right-hand side is the influent, and the pipe on the left, so it goes up and over and up and over, and then it comes out the pipe on the right-hand side, and this pipe is set below the bottom water level, so the tank never empties completely. It always is maintained between around 2/3 full and completely full. So the tank, it's hydraulically linked, the selector zone and the main aeration zone. So it'll all fill at the same time.
Right. So the biomass in your vertical tubular is overflowing or underflowing into your aerobic zone?
Yeah. So it will pass through. It will pass through the selector zone first with a contact time around, like I said, between an hour and 2 hours before being introduced into the aerobic zone, where it will be aerated, and then some of it will be recycled back again through the RAS pump.
Right. Okay. Thanks.
Thank you.
Fran, over front. Thanks.
Thanks for your nice presentation. Did you also measure the sludge volume index? Do you have some data on that?
We do have data for that actually as well. Yeah, I can. It's not in the presentation, obviously, but I can let you know.
Can you tell? Okay.
Yeah, off the top of my head, I can't
Okay,
tell you the numbers, but we have got data for that for sure.
Thank you.
Okay, we've got time for just one last question, if there's any other questions. No? Okay, well, thanks, Ben, and we'll see everybody after the break.
Thank you. Cheers.
Hello. Okay, well, welcome back, everybody. We're going to carry on with the phosphorus session. Oh, that's loud. Our first speaker for this session is Hans Wouters and Gareth Medley from Brightwork and Wastewater. I'm particularly looking forward to this one. I saw Hans's talk last year. It'd be interesting to see this technology being applied in the UK. So hopefully the technology is going to work, and we're going to join us virtually to present. So Hans, if you can hear me, over to you.
Thank you, Paul. I can hear you loud and clearly. Thank you. Thank you. It's quite a long title, which we are going to present together with Garrett. Enhanced P removal by changing design and operational parameters to meet new permits with sand filters and utilizing sand cycle. But we'll try to explain it in a way that the message comes across. What we are going to do is that, and it's already what you indicated, we've gone through a process with three projects within the Welsh area to enhance phosphorus removal in tertiary applications by using existing assets and using particular refurbishment tools and sand cycle to promote this. And in this presentation, which we do together, we would like to highlight the results of what we achieved, and also we would like to highlight what kind of roadmap is ahead of us by using these tools and using them effectively. First of all, if you look at Wastewater, their slogan, working together to achieve our measures of success, very nicely coincides with the slogan which we have as Brightwork, as a technology supplier of particular treatment components which are used in water and wastewater technology. And that is collaborating to improve your processes. What we've been doing is we have been focusing on a particular continuous sand filter process, which is indicated in this sheet, and which is basically also applied globally. In the world, more than 100,000 units have been installed at various occasions for tertiary treatment, for wastewater treatment, for water treatment, for surface water, for groundwater, for cooling water, multiple applications. If you look at the wastewater applications, then almost all the applications are tertiary applications. Tertiary applications to remove the last parts of suspended solids, BOD, phosphorus and nitrogen, and also looking at micropollutants these days, but that's a different story. There are also various makes and manufacturers of these continuous sand filters. So if you look at the playing field, I think there are more than 20, 30 different makes and shapes of continuous sand filters which are used, and some of those are working very well, some of those are not working very well, but at the end of the day, we would like to have a look at those and see what we can take out of those. The economic and environmental drivers these days are very much focused on asset management, stretching performance targets, combining operational functions, which means that, for instance, you would like to combine nitrogen removal and phosphorus removal in one and the same reactor. What we also see in the field is that the operator attendance is quite a challenge. Operators are often very much involved in a lot of wastewater treatment plants, so they have to divide their time into these different treatment plants and see how they can do that efficiently. So if we can help the operator to reduce the attendance for the treatment works and for particular treatment components, that's very helpful. And the operator tasks are also intensified. There's a challenge to stretch the applications, so the plants need to operate well and during all circumstances. So it's quite a challenge to achieve that. And I think what we try to do at two particular works within Wastewater we managed to do so, and that's well basically what we would like to show and highlight. If you look at the continuous sand filter, I think most of you might be familiar with it, but just let me briefly explain what the core operational features of the filter is that the filter is an upward flow filter. So the water flows into the filter at the bottom level, flows upward through the sand filter, and then at the top, the filtrate is released. During this process, solids or whatever you would like to retain are retained in the pores of the sand filter. And if you accumulate these solids, then at the end of the day, they will break through and pollute the filtrate. So that's not the idea. The idea is that continuously part of the sand bed containing these solids are washed and recycled back to the sand filter in a clean status. And we do that by using an airlift, which is basically a pipe in the center part of the filter, at which a little bit of compressed air is blown at the bottom section, which then starts to act as a vacuum cleaner. So it sucks in the polluted sand, the sand with the solids, into the entry of the airlift and pushes it to the top. And at the top, the sand is washed. And that washing process is a purely hydraulic process. So the water, a bit of filtrate is used to wash out the lighter solids, and the sand grains are then falling countercurrently back onto the top of the sand filter. So basically, there's a constant balance between the feed solids coming in, the filtrate, which is free of solids, and the wash water, which contains the concentrated amounts of solids. And you can imagine that if you do this in a good way, you can handle quite high solid flows, and you can also steer the process in function of the solids load by pushing more or less air into the airlift and therefore circulating more or less sand. And those kind of techniques have been applied in order to optimize systems and to use it to the very end and try to combine the functions. If you look at the installed base, a lot of these filters have been used in the past purely for solids and BOD removal. And then some anomalies have been discovered in these filter plants, which needs to be paid attention to. And part of what we've seen in the sites which we've followed up is that it's quite obvious what these anomalies are. So if you take away the issues around the filter, you'll be able to do a good job and to get out of the system what you want to get out of it. And that is something which we would like to explain in the projects which we've been doing. What I also would like to briefly touch, I will not go into the details of that too much, but it's relevant for what we've been doing at the sites, is that we started to do a survey by trying to find out what were the issues with the continuous sand filters which we investigated. And we used a very efficient tool for that, which is called Sand Cycle Monitoring and Control. And to just simply explain what it is about, is that we try to find out how homogeneous the sand is circulating throughout the filter bed. This circulation is key for the performance of the filter. So if we find out whether all the sand grains are circulating in the same way and the same pace, then we know that the circumstances are right for a proper functioning of the filter plant. How do we do that? Simply by using the technology which a cat or a dog is equipped with, and that is the RFID tag, the chip which identifies a cat when it enters a cat lock. And if the lock is then identifying the chip from your particular cat, the lock will open and the cat can enter. The neighbor's cat cannot enter because he has a chip with a different number. This particular principle we used to get more out of the filter, to find out whether a filter is functioning properly or not. We just simply throw in these tags into the filter bed, and these tags are then moving as if they were sand grains. So each time they pass the airlift, they will be pushed to the top, they will be washed as well, and fall back onto the sand bed, as if they were sand grains. Each time when they pass the antennae, the tag number and the timestamp will be collected. And this data set allows us to generate dashboards which show whether the filter is functioning properly or not. And this proves to be a very powerful tool to analyze any existing assets and see whether these assets are functioning properly or whether there's any room for improvement. If you look at a particular filter, I've indicated in this sheet, 3 to 5 tags per cubic meter of filter bed volume is enough to create enough data for us to do some statistical analysis. And that allows us then to find out how the system is running. We do that continuously, and we can use those continuous data sets to help the operator to understand how the system is running and whether to intervene if and when required. The advantages are obvious. We can stretch filter applications, we can improve filter performance, we can higher the uptime. Also, quite important is a longer lifetime of wear and tear parts, energy savings and some chemical savings, and maybe the most important one is reduced and focused operator attendance, where he can just now see what is going on with his filter plant and intervene there where he needs to intervene. I won't go into too much of the details of the technology, but the system looks like this. So you have the filters on the top left corner, equipped with the tags. The data sets, the timestamps and the tag numbers are recorded and pushed to the data logger, to our web server, and then back into a dashboard. And the dashboards will come by in the rest of the presentation. Left down corner, there's a set of 4 antennae, which are vital, of course, to pick up the signals. Then we have 2 case studies, which I think might be interesting to share with you, where we actually started by investigating what the present situation of the filters were, to find out whether it makes sense to refurbish these filters. And we used SendCycle as part of that analysis, as part of that survey, to make a plan of action. On the left-hand side, there is the Glamberis wastewater treatment plant with the phosphorus removal filters. On the right-hand side is the Whitchurch wastewater treatment plant equipped with 4 polishing filters. And I would like now to give the word to Gerrit to explain a bit more what has been done there and what the results were.
Thank you, Hans. Okay, so looking at Whitchurch for tertiary solids removal, this was again an existing plant, as Hans mentioned, with 4 filters. There's currently an offline asset due to some operational issues with the filters. As part of the innovation portfolio back in 2017, 2018, SendCycle was installed on filter number 1, exactly as Hans said, to get some diagnosis of the problems, and that put into plan some upgrade targets. The original flow capacity to each filter was 14 litres per second. The refurbishment plan and the information that came back from the innovation trial showed that with the upgrades that Brightwork were recommending, and indeed the data that we were getting back from that trial, 25 litres per second was achievable through each of the sand filters. Now this aligns with Wastewater's 2040 growth horizon strategy, without the need for new build of a new TSR bank or indeed additional filters. Also, in the midpoint of this AMP, the total P consent is reducing from 1 milligram per litre to 0.3, which is quite a significant jump. At the moment, only primary ferric is dosed on site, but there is a capacity for secondary and tertiary dosing. So the timeline at the moment is to put those into place to achieve the incoming reduction of total P consent. So the timeline was, as I mentioned, we did the innovation trial in 2018, refurbished all of the filters last year in 2020, and successful commissioning came online October of last year. Unfortunately, it does say 2021 at the bottom of that one, but there we are. So that's a bit of a background for Whitchurch. So here is, this was the diagnostic phase from the first trial. Hans, would you like to just talk a little bit more about what this graph is showing?
I can do. What you see in this diagram is that we followed the tags which we brought into this filter number 1, and we started to analyze how often these tags came by and in what kind of speed they came by. And this has been plotted in a graph which gives you the particular tags on the y-axis and the time it takes for each particular tag to do one cycle. So that means it falls from the washer onto the top of the sandbed, then travels all the way down towards the entry of the airlift, and then it's pushed to the top of the filter again. So each cycle is well, there's a time frame of a couple of hours, which is expressed on the x-axis. And what you see here, and that is particularly relevant for let's say having a decent continuous sand filter, is that there is a wide variety of the cycle times. It starts with on the left-hand side 3.5 hours or 3 hours, and it goes up to even 30 hours. So that's a range where you can't speak about a homogeneous sand circulation. It's very inhomogeneous, and an inhomogeneous sand circulation means is that part of the filter bed will move quickly, and the other parts will almost stay where they are, and that will directly impact the filter performance. And that's actually what we've seen in stages before we did the diagnosis, is that the filters were not performing very well. So that was the starting point to say, okay, if this is the case, how can we improve the situation and make this filter run in such a mode that it will have homogeneous sand circulation rates in a range where we would like to have it. So this is from the diagnosis point of view. If you then continue, maybe Garrett, you would like to explain this graph?
Yeah. So this is the forward-facing dashboard towards operations and any teams that use Sand Cycle, giving a nice graphical representation of average circulation speed, filter homogeneity, and a rag status. Obviously, red is bad, amber, highlighting that things may be moving in either direction towards bad and good, and green obviously is where you want to be. The last activity, i.e. the last time a tag passed the decoder in the airlift, active bed volume, sand circulation, and you can call up and actually download all of the timestamps on the measurements on the left-hand side if you want to do your own analysis, etc., or marry that up to anything else. So yeah, easy to use, and on the actual page, you have all the operational manuals, etc., as a drop down, so you can be anywhere dial in remotely on a tablet or a phone and get help, and also see the dashboards from wherever you are.
Maybe it's good to add to that, Garrett, is that in the graph, you'll see the blue line, which is indicating the actual average sand circulation rate, which is in this case around 4 millimeters per minute. And you'll see quite a horizontal line. But what is even more interesting is to look at the, let's say, the cloud area around the blue line, because this cloud area indicates where the maximum circulation time and the minimum circulation time of the tags are within. And this line, this cloud, should be, more or less coincide with the average line. If it's starting to divert, you know that something is going wrong, and that's not what you want. So actually, if you project this graph on the pre-refurbished sand filters, then it was a very irregular pattern of very irregular sand circulation rates with clouds all around, indicating that the homogeneous sand circulation is nowhere near. And this indicates the opposite. This was a screenshot of the, let's say, October 2020 after commissioning period. Garrett.
In terms, so looking at some final effluent data taken by operations, it's not official OSM data. You can see the red line is when the sand filters came online and were in service. Prior to that, the site struggling with final effluent suspended solids. Obviously, there's associated elevation of total P with that. And then after commissioning and all 4 filters being in service and all flow going through them, quite a reduction of the suspended solids within the final effluent. And of course, this is where we want to be with regards to turning on secondary and potentially tertiary ferric dosing to reduce that even more, and particularly the total phosphorus in the final effluent. So looking at Lamberis now, 2 filters for tertiary P removal. The capacity of each filter 10 litres per second. The consent is 0.5 milligrams per litre, but there's an operating and an agreement with the regulator to operate at around about 0.2. However, most instances phosphorus is removed to undetectable levels. Again, the driver's in-depth diagnosis of the filters, the refurbishment plan and costs. Particular target is these very, very low Ps in the final effluent, and also better recovery of residual iron in the final effluent, of which you'll see some data when the site was on primary and secondary ferric dosing whilst the sand filters were offline for refurbishment. So these were diagnosed in 2019. As I said, refurbishment of both filters happened in 2021, and the commissioning was on July this year, 2021. Again, another example of the dashboard for filter number 1 at Lamberis, and some final effluent data with regards to total P, suspended solids, and iron. And what's really interesting is that although total phosphorus was really low in both scenarios, so the left-hand side of the line is on primary and secondary ferric dosing only, and then with the filters coming online in July, you can see a massive reduction in the iron residual and indeed suspended solids in the final effluent, and this continued line of the phosphate removal, and as I said, total phosphorus levels are below levels of detection in lab-based equipment.
Gareth, just 1 minute, please. Thanks.
Yep, we'll catch up.
What was that, sorry?
It was 1 minute left.
Okay, right.
So I have
Okay,
to catch up.
Okay, right. Oh, so sorry. So the big takeaway here is the reduction in chemical usage just from tertiary ferric dose sand filters. So we reduced down from 8 litres per hour on ferric down to 3 to 4 litres per hour, flow dependent. And caustic reduction. Caustic was used for pH correction in the primary and secondary scenario, and now a small trim is used for suppression of the wash waters from the sand filters, and some is used for correct alkalinity correction for phosphorus removal in the sand filters themselves. But the big takeaway is obviously a much better use of ferric, very pertinent at the moment with regards to chemical availability and indeed distribution across the UK. So a much more efficient use of ferric coagulants in the asset.
That was a little bit more than 1 minute, so I will catch up very rapidly. I think we try to express the successful refurbishment of some existing assets, which saves costs and which gives the operator quite a good support in trying to keep the units in good shape and in good performance. And as Garrett already indicated, is the tertiary coagulant dosing proves to be highly effective with the chemical consumption, which can be reduced. I think this is a nice example of a consistent collaboration between a water utility operator and a tax supplier, and that's what we would like to share with you. Thank you very much for your attendance.
Thank you.
Thanks, Hans and Gareth. Really interesting, and interesting to see how we can use data like that to get insights into something where normally we can't really see inside and see what's actually going on. So, just a quick question from Catherine Balfeld here saying, did the RFID tags really represent the sand particle behaviour in terms of size, weight, etc.? Great idea, but how to apply actual sand particle behaviour? So, I mean, the graphs and the data look good, so I assume that you've kind of validated it in terms of how the tags behave?
Yes, indeed. Well, it's a very good question, because that's what we started with when we got this idea, is how can we simulate the sand grain's movement. The density of the tags are similar because it's a glass capsule with the same density as a sand grain. Of course, they are not similar in size. They are a bit bigger than a sand grain, but as they are inside, let's say, a packed bed, they will behave or they will move like any other sand grain inside the reactor. So that helps in simulating the behavior of the sand in the reactor, and also the washing process and the process of getting these tags up into the airlift and pushed to the top. There is no let's say deviation from what a sand grain does. So it's a good proxy for the sand grain movement, and therefore also a good proxy in starting to find out how the unit is running.
Okay, great. And I think because of time we have to move on, but if people want to carry on the Q&A for that online, then please continue to kind of pop any questions or just on the platform there. So
we're happy to answer.
Yeah, so thanks again.
Thank you.
Okay, so our next speaker is Narinder Sunna, and he's going to be telling us not to forget the basics of chemical phosphorus removal.
Thanks, Paul. Can everybody hear me? Yeah? Okay, great. It's actually really good to be here, and you realise there are others, and so it's great. And a lot of people, you know, I'm sure you've probably met for the first time, face to face. I've met a lot of people here already, and that I've only sort of met on a team site. And remarkably, they actually look very similar to the online version. So it's great that everybody's here. So we as an industry, we probably haven't been sort of as impacted by COVID as others. So if you can, everybody go out there, spend your money, and let's get the sort of the economy rolling. So great to see everybody. So I'm going to talk about the basics of chemical phosphorus removal. And it's probably worthwhile just giving a bit of background around this and where our clients actually are. So if you can imagine, you get your off-watt emission, you get £1. You get £1. What the regulator does is the regulator will take 20-30% away from you straight away. So you end up with 80 pence. And then where we are as an industry now is we've probably got about 50 pence because inflation's been running at around 25 to 30%. We've got around 50 pence to deliver something that's going to cost £1. Okay? And so where the industry sort of ended up is we're having to use ferric dosing, which I know a lot of you out there aren't big fans of. I'm not a big fan of it neither. But that's where we are as an industry. And we just need to get the basics of chemical phosphorus removal right. And so that's what my presentation's really about. So, yeah, there's my intro. So we're going to continue to rely on ferric dosing. I'm going to talk about some of the applications, experiences in AMP6, good, bad, ugly practice, and then sort of just finish up with a summary and conclusion. So this is where we are with ferric dosing. Probably, you know, it's the easiest thing to do, isn't it? You know, it's tried, it's tested, you throw it in there. So typically, it's the lowest capex, lowest OPEX, you know, yes and no, depending on what frameworks have been signed up with the various manufacturers. Whole life cost, lowest whole life cost. Again, typically yes, but depending on how our lovely clients look at whole life cost. Is it 20 years, 40 years, 60 years, 80 years, 100 years? It sort of very much varies. And in terms of embedded carbon, definitely, it's probably the lowest embedded carbon. And, you know, the other advantage is there's no N2O production. So the big question out there at the moment is all about N2O production. So you go down the BioP route, does it generate N2O? How much does it generate? We actually don't really know. And so that's probably another reason why a lot of clients are going to, you know, sticking with ferric dosing. You all know, you know, you're absolute experts out there, aren't you? The two chemicals we typically use, ferric chloride, ferric sulfate. Ferric chloride on septic sewage, ferric sulfate normally on you know, normal incoming sewage. You dose it, and bang, you settle it and you filter it depending on where you actually apply it. Typical units, so that's a WES unit, you know, tiny little unit, about a cubic meter. Pretty cheap, it's cheap as chips, separate dosing packages. Here's another type of arrangement, and here what you've got is on the right hand side, you've got your ferric dosing, you've got your shower in the centre, and then towards the left you've got a typical sort of tertiary treatment process, which here is a Meccana, and that Meccana will also have some form of ferric dose, and you'll probably end up with 2-point dose, ferric into the primary tank, and another dosing set that's dosing into the tertiary treatment. And, you know, again, everybody's seen this slide, but I want to bring it up time after time. And what this slide shows is that we're predicting that ferric is actually going to become a bit of an issue in terms of supply. And so the current usage is about 450,000 tonnes. Current capacity is 550, and future usage, so by AMP, by the end of the AMP, will be up to 750. So if you imagine, a lot of the sites will be commissioned probably 2023 going into 2024, because that's when a lot of the reg outputs are. It's going to create a bit of an issue, and already we're seeing some, you know, there's very little resilience in this whole marketplace. You've seen how a few HGV drivers have impacted ferric. So overall, it's going to continue, and it's probably this whole ferric issue is going to become a bit of a risk if we don't engage with the supply chain and let them know that that's how much we actually need. Currently, they don't know that that's how much production is required by the industry as a whole, because again, what will happen is the way they communicate with the supply chain is very differently. So each individual water company will tell them probably 6 months before, this is what I need. But guess what? There's not that capacity there. Just talking about how we normally dose. So typically for a P of less than 0.5, it's a 2-point dose, pre-primary or pre-humus, into ASP reactors, pre-FSTs, pre-tertiary. And there's always a top-up dose for your BioP, ASPs and Nerida as well. And with tertiary treatment processes, again, ferric dosing will be used, and this is a typical list of various technologies. So we've got cloth pile filters, filter clears, deep bed sound filters, moving bed, reed beds, Nerida, Comag, Biomag, reed beds, disc filters. So it's all the processes mainly will use some form of top-up dose regardless. And here are some typical mixing requirements in client asset standards. So watts per cubic meter, COV, coefficient of velocity. So watts per cubic meter is normally about 100-ish. COV less than 0.05. And then, of course, a number of clients will just use visual checks. And here, what tends to happen is you just need to ensure that your visual checks are done under not only peak weather conditions where you've got increased flow, but also dry weather flow. So again, a lot of people being caught out where under dry weather flow conditions, it looks fine. But when you get to peak flow, there's no hydraulic jump or anything else like that. And then, of course, CFD modelling as well. And what we've seen is those standards haven't been applied consistently. And so this is I've got lots of pictures, by the way. So this is an ugly example of ferric dosing. And so what you have here is you have the ferric dose, which is, I'm going to go across there. And here, the mixing energy is actually provided by a pump system, which is there. And what you can see is that's the worst case of mixing I have ever seen, ever. So, and you think this is a one-off. When you look at multiple sites, it's actually endemic. So one thing we've done as an industry is we haven't looked at the basics, and the basics here, get the mixing right. And it's not rocket science, to be honest. And again, this is quite a bad example, again, for me, and this is primary desludging. And so primary, effectively what we're relying on, you get good mixing and you remove the sludge. Guess what? It's possible to achieve these standards and reduce your chemical usage. So who drove at 60 miles an hour this morning? None of you. I drove at 60 miles an hour, and guess what? I got a lot more out of my tank. And all these little measures can help with reducing your ferric use. And so this is a desludge system here, and it's absolutely on its last legs. So if you're going to do the minimum, good mixing, desludging, that will get a lot of those solids out. It'll remove metals consent risk, etc. And one giveaway for excessive chemical use is actually having a look at how much chemicals being used compared to the kilograms of phosphorus that are coming in. So this is one typical site. And honestly, I've got 20, 30 similar graphics showing how inefficient mixing and desludging has been. So here, well and good, you start off with quite a high dose at the front end. But what you see here, and it continued forever, was the fact that we ended up with using 3 kilogram of Fe per kilogram of P throughout for the next year or so. So again, it's a good telltale sign that the mixing isn't right, or your desludging isn't right, or there's something not quite right on a particular site. And you know, again, just to remind everybody, what does good mixing look like? And this is one of the best examples I've seen, and this is actually from a United Utilities site. And what you can see is effectively you've got an evenly distributed flow of ferric straight across, and then you've got a really good hydraulic jump where the mixing can happen really well, and thereafter you've got a good retention time for flocculation to actually happen. So that is not happening out there, and that's why we're using so much more ferric than we should. And again, very early on in the presentation, I talked about secondary ferric dosing. And again, this hasn't really been consistent. And again, this is really good practice, is to have proper coagulation, flocculation. So coagulation, quick mixing, flocculation, slow mixing, and extended retention times, so you get the flocks going, so get the best out of your ferric. And so these are some good examples of coagulation, flocculation. So the top picture is effectively ahead of a humus tank, and then the one to the right is effectively ahead of a Makana plant. And again, here's some, if we need to go larger, these are some examples of good flocculation, coagulation for larger sites. So again, it's getting the best out of your assets. And if you get that right, this is what you can achieve. And so this site is a single ferric dose into a primary tank. And so this site has been operating since AMP4. And so this is what can be achieved. So this is one of the sites that I was involved in, AMP4. I went back and looked at the data over many years, and this is what can be achieved. So this particular site, what we've got is we've got a site which is achieving well below a 0.5. So you get the basics right. Do you need tertiary treatment? So Jeff, I know you like selling tertiary treatment plants, yeah? It's your bread and butter, but you get it right and you can actually achieve these relatively low limits. And so I would challenge everybody around the way that we actually put in ferric dosing tertiary treatment. And I know, Martin, that within Yorkshire, it's very different. Everything's phased to get the best out of those assets, and then phase that particular. But this is what can be achieved with just some good basic understanding. So good mixing, good desludging, and good operation. And so this mixing issue has been a bugbear of mine for a long time, and I'm not too sure if Adam Coley's here from ATAC, but effectively it's been a bugbear, and there was nothing on the market for these really small sites around mixing. And so what I've done is I've actually developed a little package system which is it costs around £3,500, and it's for small sites. And of course, that £3,500, by the time you add your consultants' fees, your design costs, your prelims, it'll probably be about £1 million, but it's meant to be really, really cost effective. And it's a little diaphragm pump, and it just makes a big difference. And so one of the ways we've dropped the amount of ferric that's been used is to actually go back and retrofit this solution into those sites, and we've seen the ferric actually drop big time. So this is meant to be a video. I'm hoping this is going to work. And it works. I'm amazed. And so this was the pilot study. And so there's the little box, powered up. And so there are simple solutions out there. And in terms of payback, we're talking literally months in terms of getting payback on good mixing. That's one of the solutions. I'm sure the industry will go through and develop a lot more, but that's where we should be going. So just remember the basics. And so this is a slide I've stolen from Yorkshire Water. And this is where I think they absolutely practice this. And this is effectively, I think we need to apply the TOTEX hierarchy, and which is all about eliminating, and I think for me it's operating your assets as best as you can, invigorating those assets. So that is putting mixing and things in like that. And then that allows you to build less, build smart, and ultimately, you have to decommission assets as well at the same time. But that's the approach, and that whole phasing approach, just to get the best out of your assets by providing good mixing, good desludging, etc., is definitely the way to go. And, again, I don't, we need to remember, so as an industry, we've been so slow in developing the technologies we needed. So we're still going down the ferric dosing route, and really a lot of these technologies, we should have been developing these 10 years ago. And unfortunately, it's probably too late for this AMP. As we go into AMP8, the number of fossil schemes is going to actually drop quite tremendously. So we're stuck with what we've got, and what we're stuck with is a lot of ferric dosing. And so, in terms of technology coming through, we've got, and I've got loads of representatives here, electrocoagulation, we've got, algae treatment. And again, it's a fun, if anybody's gone to site, the algae treatment is absolutely mind-blowing. And if we'd had it 10 years ago, it would have been great. But, we are where we are. And then we've got next generation of technology, such as microvy. Again, it's imprisoning. I'm sure there's some social human rights lawyer here who will argue we shouldn't imprison these bacteria, but they're imprisoned, and they are quite effective in terms of removing phosphorus. Okay, and then just to summarise and really provide a conclusion. I think the industry, we've been using ferric dosing now for 25 years, over 25 years, but basic requirements for good mixing separation have been missed. Investment in good mixing can avoid the need for tertiary treatment and avoid associated compliance risk. In doubt, install mixing. So that's me.
Thanks, Navinda. Excellent talk. I've got one quick comment on the top-up dosing slide. When you mentioned Nevada, we've now got 13 of our 14 sites operating without chemicals through kind of ongoing optimization. So, but yeah, I'm sure there must be plenty of questions there. We've got one at the front. Yeah.
Hi, Narinder. Thank you for the presentation. Mamata Visam, Southern Water. As you might know, we are heavily reliant on ferric on most of our small to medium sites. And there is a notion, I think, within the industry, and we had a recent comment from one of our principal engineers within the business, that if there is no push enough from Ofwat and Environment Agency to move away from ferric dosing, then where do water industries stand in that perspective?
I know.
So it's really, I mean, like you said, electrocoagulation, everything is brilliant. We have done some trials with micro-V and everything. When it comes to balancing the business cases, like going back to your first comment you made about 50p and £1, that's where everything's falling back.
It is.
So it's really hard. So I think we are sort of now thinking that we need to really align with our strategic priorities and say, in 20 years' time, do we really want to use ferric dosing just because EA is not pushing us towards it? Or should we make a decision and say, no, actually, we are going to save a bit now, and in 20 years' time, we want to install this technology and remove ferric dosing? So I think it's a really big challenge for water industries, to be really honest.
No, absolutely. Absolutely. And I'll tell you where. So we estimate that we're going to be spending £20 billion in AMP 8 and 9 on storm overflows. These storm overflows have very little impact on the river quality, but yet the public perception is that we need to spend £20 billion, add £25 to customer bills to enable that to happen. And so it's for me, it is just having that conversation with the people who pay the bills, because it's really weird. They don't actually care about the quality of the rivers. What they care about is those storm overflows. And it's just having that conversation and probably educating that whole next generation around what their money is actually providing and the need to go to more sustainable types of solutions. So it's a big journey we're on. So one of the things that I'm going to be kicking off is just getting that education. We'll never get it into, we'll probably get into your generation, but we need to get it into our kids' generation, because they are the future bill payers, and they need to understand the detail behind some of these decisions, really. Because I personally think that £25 increase in bills because of storm overflows is better spent becoming a more sustainable industry and getting away from ferric.
But saying that, I have made small changes. So 2 of my sites have now got ATAX ferric mixing. So they've improved our ferric mixing. So I'm just awaiting the results. And from what you have presented today, I think I'll be keeping an eye how it improves the whole process.
Yeah.
Lovely. Thank you.
I've got a question at the back.
Just before that, I've just got a quick question for you, actually, Navinda, which is, I just wonder what your thoughts were on, you mentioned a lot about mixing, but in terms of how we control multi-point dosing. I mean, I've seen a few sites where the tendency of operators, because they don't want to fail consent, is to put more chemical in at the first point, sometimes to a detriment of a biological stage. You take all phosphorus out, just because I think the quicker I can get the phosphorus out, the less risk there is of consent failure. Do you think there's more that should be done around how we either control or train people, or?
Yeah, no, absolutely. And I think there are lots of different ways of controlling phosphorus. And I think for me, one of the best ways is actually something that I sort of put into Southern Water, which is P instrument goes in first, and effectively that pre-instrument effectively gives you the profile of the dosing that's actually required. And that's really, really good practice, because then you're able to look at the various scenarios, wet weather, dry weather, various scenarios, and you can literally adjust your profile based on weather conditions.
Yeah, that sounds a good philosophy, definitely. Was there one last question? Okay,
Hi, Narinder. It's Shahad from Severn Trent. Quick question about chemical rare earth. Has that been considered? Because I know there's a huge impact on using ferric sulfate in our works, and looking at innovation technologies, which we are discussing at the moment and implementing in our works. However, some sites you have to use chemical for P removal, and now rare earth is one of the new chemicals that is being approached and looked at, and and we are in discussions with EA about applying it to some of our sites. So I was wondering if there's any work with other water industries. Have anybody looked at it or even consider it on their sites? Because it has some advantages. However, it's not quite available in the market.
Yeah. I'd actually open that up to yourself.
Me?
Yeah. So are Southern Water considering it?
The green chemicals?
Yeah.
Very early stages, we're doing some jar tests. So it is something on our radar. But again, EA is a blocker in many ways because we're not trying to get to that. I don't know whether you guys have had that conversation with EA. We haven't come to that stage yet. So we are definitely thinking about alternatives and considering green chemicals.
So I think, yes, so I think that was what I wanted to say, is that we are talking with EA at the moment. We have some response from EA, but I think that the chemical rare earth is a new chemical that needed to be added to the batch of chemicals, because again, we are all striving to reduce the reliance on chemical. However, we'll be faced with some challenges that we will have to implement them on some sites.
Yeah.
It's about the 10 times the price though. That's the other thing we have to really weigh out and how much we're going to use.
Yeah, and I think the other thing that's come up is, I have these same conversations with every single water company. And, again, it'd be great if we could sort of coordinate with the Environment Agency to have that one sort of discussion.
Sorry, we tried to do a trial for Leominster, which we've had to delay. We're still pursuing it, and we're still having discussions this week again, because as far as we're concerned, it's going to save us a lot of money and chemical usage. So we're still, as far as we're concerned, is a joined up approach with the regulator. It just might not be all the right people in the meeting.
So it sounds like this could almost do a separate discussion. But yeah, so I think, time to move on. So thanks again, Navinda.
Yeah,
excellent.
Thank you.
Thank you.
Thanks, guys.
Okay, so next up, Caroline Ho of Blue Water Bio will be talking about phosphorus removal using Filter Clear.
Thank you, Paul, and good afternoon, everyone. It's so good for you to join this session. And today, my talk is about phosphorus removal using Filter Clear, which provide operational flexibility and reliability. And we're now in the second year of M7, so I'm sure people will appreciate the tertiary plant they put into for P removal will offer these benefits. And also, we're going to share with you some lessons learned on caustic dosing. Wendy from MMB will be co-presenting with me today. So I will start with a quick introduction of UU's P removal program in M7, and then focusing on a site called Barton, where we installed a Filter Clear plant for P removal. You will see the performance of that with the conventional 2-point ferric dosing. And then Wendy will talk about the problem we have on site with caustic dosing, and then how it was resolved step by step. And after that, you will see the result of P removal with single-point ferric dosing. And finally, the conclusions and the recommendations we have. So this is UU's catchment on the northwest of the country. You can see there are many large cities. And in M7, UU's P program have over 70 sites. 50 of those sites will have it's new to P removal, and the majority of the sites will have a TP consent at 0.5 or below. And Barton is one of this site. It's treating a population over 8,000, and the TP permit is 0.5 ppm, and the total iron is 4 ppm. So the site is quite typical. Start with inlet works, and then primary settlement tanks, SAF to provide BOD removal, followed by trickling filters and the humus tanks. And then part of the flow will go through a nitrifying filter to ensure the ammonium consent. And finally, the filter clear for P removal. So the crude sewage also P is monitored online, and we use this to control the first point ferric dosing before the primary tanks. Caustic dosing, we're using sodium hydroxide to top up the alkalinity for the downstream nitrification, and that was applied after the primary tanks. So the second point ferric dosing was before the filter clear plant into a static mixer. A quick overview of the filter clear plant. It's a depth filtration with 900 ml of media depth. So the flow enters the filter from the top and then flows through 4 layers of media. From top to bottom, they are anthracite, sand, alumina, and magnetite. So each layer is finer than the media above, and this is how we achieve the really good effluent quality at a very high filtration rate. So you will notice the filtration rate is around 25 to 35 meter per hour, which is much higher than your normal sand filter. Because the solids are removed through the entire depth of the media bed, so we can increase the solid holding capacity and extend the filter runtime, which will reduce your backwash demand. The backwash is controlled on timer or pressure, and then after backwash, each media will settle to its original layer because we got this increasing density of the media from top to bottom. And for P removal, we don't need flocculation tank or polymer dosing. The second point ferric dosing can be added into an inline static mixer before the filter clear plant. So the flocculation will happen inside filter clear in the head space above the media bed. The operating pressure is around 0.5 bar, so it's quite a low power consumption. And you can see the filter is enclosed, so it's very safe and easy for operator to operate and maintain. And the design is modular, so easy to scale up. And this is the filter clear plant we installed in Barton. And there are 3 filters with a clean tank and a dirty tank. MCC is on the right-hand side. You can see from the top photo. And then the filter, the second point ferric dosing, you can see is added into the static mixer, leading to the filter clear plant. And we adopt a DFMA approach. So that means the filter clear plant is manufactured and tested off-site, and this will and taken to the site as an entire package plant. So this will speed up your installation and the commissioning, and also, will ensure the quality control and shorten your construction time and reduce your health and safety risk on site. The plant was designed with the 2-point ferric dosing in mind. So the first point ferric dosing we showed before was upstream of the primary tanks. And because we monitor the crude sewage also P together with the flow rate, so we're actually controlling the first point dosing on the P load based, and it's a feed forward control. The dosing molar ratio is around 2.5 on average. And the second point dosing is before the filter clear plant into the static mixer. The dosing control here is flow proportional and assuming that a fairly constant TP can be achieved by the first point dosing. So the second point dosing molar ratio is around 4 on average. And the filter is backwashed 3 times a day on timer. And the caustic dosing we showed before is a single point dosing into the primary tank effluent, and that the dosing rate is in proportional to the combined rate of the 2-point ferric dosing. And this is the performance data after the, during the performance test. So the commissioning was early last year during the first lockdown, and we were against a very tight regulatory deadline. The first point ferric dosing was only turned on 2 weeks before the regulatory deadline, and then the second point ferric dosing was switched on just a week before. So you can see that there wasn't much time for optimization. But the filter clear plant responded quickly, so the effluent from the filter clear dropped from 0.6 ppm down below to 0.2 very quickly. And you can see both the TP and the iron were very much below the consent requirement with a good safety margin. So far so good, but then suddenly something happened, and Wendy will talk you through to that.
Right, thanks, Caroline. Yeah, so we've got great performance basically from Barton, but site operators started to come to us saying they're having problems with their SAF feed pumps, and you can see on the photos some of the issues that we were having. Basically, they were getting reduced flow rates up to the SAFs, and the pumps themselves are starting to fail. So the photo on the left is scale deposits are actually chipped off the impellers of the pumps, and you can see the reduced diameter in the rising mains. So we basically sent a sample off to be tested, and that came back that we'd got calcium carbonate scaling along with some ferric sulfate and oxide deposits. So basically we had quite a major scaling problem on our hands. So if we just take an aside and look at the Langelier saturation index, which is an indication of a solution's ability to dissolve or deposit calcium carbonate. So the main factors influencing this are the alkalinity, pH, calcium concentration, total dissolved solids, and temperature. So if you have an LSI less than 0, then your water is likely to be corrosive and dissolve calcium carbonate. A value greater than 0 means that it's likely to be scale forming. So basically we started to investigate this. We did some site sampling and testing, measuring calcium, pH, temperature, alkalinity in the water. We took that data along with flow data, chemical dosing flow rates, and used a sort of water mixing calculation tool from our clean water colleagues, and then sort of looked at the predicted results from that compared to the measured results. You can see the results in the table for the SAF feed pumping station. We'd got good agreement between measured and predicted, and an LSI well above 0, so it wasn't surprising that we had a scaling problem. So what could we do about this problem? The high pH in the SAF feed was really the driving force for the scaling that was happening. We felt if we could reduce the amount of caustic that we were dosing, we would hopefully reduce that pH and solve the problem. We were dosing significant quantities of caustic to balance both the primary and the secondary ferric doses, as as Caroline was saying. So our first thoughts were to stop that second ferric dose. At another UU site, we were achieving the 0.5 total phosphorus with single point dosing, and we had results from the humus tank effluent at Barton, which indicated we could do it there as well. Other options, obviously lots of discussions going on. Do we need to improve the mixing? Back to Narinda's point. Looking at different points of application. Would we need to change the chemical? Obviously that would be worst case because we've just invested and installed the caustic dosing. And all the time sort of looking to improve the calculations so we could try and predict what would happen on site. So just looking at the amount of caustic that we're dosing, you can see the green lines are the caustic on the left-hand graph, and the dark brown is the primary ferric. So the first sort of set of bars is with the 2-point dosing. So we're putting significant amounts of caustic in comparison to the primary ferric. The blue bars give you the ratio of caustic to primary ferric. So during the 2-point dosing, we were averaging over twice as much caustic by volume as ferric. And some of the time that was peaking up to 3. This is because of the flow proportional dosing at the back end. So we took out, in the calculation, we took out the secondary ferric dose. It indicated that we should solve the scaling problem, but actually, sadly, that didn't happen. We still had scaling, we still had high pH. So looking at the POA, on the left, you've got the actual POA. It's into quite a small chamber. There weren't too many options on this site for where the dosing would be. We had a jet off the SAF rising main coming back into the chamber to try and sort of ensure mixing, but we weren't really confident that was being effective. In the middle photo, you can see that the POA is just in the background, and then the flow sort of comes straight into the SAF feed pumping station. It comes in at low level. Any flow that the SAFs don't pump up, the pumps don't pump up to the SAFs, will overflow directly into the downstream mineral filter feed distribution chamber. So we were thinking that perhaps with the density of the caustic, we were getting sort of preferential flow of the caustic straight through to the SAF feed pumping station. We put an additional pump in the POA chamber to ensure mixing in there, but still we haven't resolved the problem. So looking at different POAs, we considered, can we put the caustic in at the inlet works with the ferric, at the SAF inlets, or even at the SAF outlets. The Jacopa SAFs, we sort of consulted with them. They were obviously concerned that we just moved the scaling problem into the SAF if we dosed at the inlet of the SAF, potentially impacting on the fine bubble diffused aerators. Post-SAF, it was practically very difficult on site. There were no open chambers, but then really we were concerned that we potentially put high pH onto the mineral filters, which obviously we couldn't have. So the model now is giving us a bit more, sort of people who worked on it, a bit more confidence at the inlet works. If we move the caustic to the inlet works, that would get the pH as low as it needed to be. And that actually was the case. We did a temporary move of one of the dosing lines to the inlet works, and success, we managed to sort of solve that scaling problem. So I think back to Caroline with the results of what that actually meant in terms of peer removal.
Thanks. And so now you can see the peer removal performance over the last 14 months. The first 7 months, we were applying 2-point ferric dosing, And then the filter clear effluent P was very much below 0.2 with an average at 0.1. So this is very much overachieving. And then, as Wendy said, we stopped the second point dosing to reduce the alkalinity demand. And then, as expected, the TP will improve accordingly, but still very much below the consent requirement, averaging at 0.3. And these are the spot samples taken over the last 14 months. It would be good to know what is the P removal achieved by each stage of the treatment. And for that purpose, composite samples were collected, and the results are summarized here. So the table on the left shows the performance at each stage with 2-point ferric dosing, and that was last April. So you can see the incoming flow are quite strong, with a TP concentration averaging at around 9 ppm, and the filter clear influent TP, just point here. So filter clear influent and filter clear effluent TP, and you can see it's still quite strong, over 1.4, but the filter clear effluent TP was below 0.2. And then just looking at the filter clear TP removal at the second point, so we have 87% P removal achieved by filter clear. And when the second point dosing was switched off, you can see the performance on the table on the right-hand side. And this was collected April this year. And you can see the incoming sewage are quite similar to last year, around 9 milligram per liter TP. And then the filter clear influent dropped down to around 1 milligram per liter, and the effluent is over 0.3. And without second point ferric dosing, you can see filter clear still achieved a percentage removal of 65%. So from here, like the previous talk saying, you really don't need second point dosing. That will be site specific. But then the tertiary treatment plant is still essential, because otherwise the effluent will be around 1 ppm, while the consent is 0.5. Another benefit of single point ferric dosing is the effluent ion is very much reduced. You can see on the table on the right-hand side, that's 0.4 in comparison to the 1.3 with 2-point ferric dosing. So this is a good news. And finally, the conclusions. So the site achieved TP consent reliably, and more than that, filter clear also offer the flexibility of achieving this TP consent with single point ferric dosing, and the benefit including the chemical cost saving, both for ferric and caustic. Like the slides earlier shows, the ferric dosing saving about 30%, and the caustic dosing halved, with single point ferric dosing. And the lower effluent ion, I think that's welcomed by all the water companies, and also it simplifies the dosing and the control. And also because without second point dosing, the solids loading to the filter clear plant will be reduced, and then the backwash demand will be reduced. And because with filter clear, you've got this flexibility to achieve a much lower consent. So if in the future there's a consent tightening on site, you can simply switch on the second point dosing. Right, Randy?
Thanks. Oh, I don't need that. Yeah, so just sort of drawing together some of the lessons from the caustic. Obviously, to a certain extent, we were fortunate. We were still on site when this scaling problem occurred. So that was picked up quite early. So it did give the opportunity to do a bit more optimisation of the site, the dosing in terms of the ferric, whilst we were solving the scaling problem. This might seem an obvious thing to say, but consider scaling potential in the design. We had considered it in terms of the actual caustic rig itself. We put a lower strength caustic in than we had at other sites. Some sites with softer water would use 47% caustic and then diluted it before dosing. So there was a specific decision to go with the lower percentage caustic, but we hadn't anticipated that there could be a problem on site after dosing. I think more extensive jar testing is often worthwhile, particularly looking at what the impact on pH that the ferric dose has, and then sort of following that up with how can you get sufficient alkalinity in that water while still keeping within a pH range that's acceptable to the site. Mixing has been well talked about. It's obviously just as important with the caustic dosing as with the ferric dosing. And certainly want to avoid areas of high pH that could act as sort of nucleation sites for scaling. So we've seen at Barton that co-locating the caustic dose with the ferric dose has been successful in solving the scaling, but also there was no detriment to the total phosphorus removal. We didn't need to add any extra quantities of chemicals for that, for that single dose. So I think that's a positive thing to take away from there. Oops, sorry. And then back to, if we're dosing ferric in two places, it's on certain works, it's going to be very difficult to put enough alkalinity into dose to balance both those doses. So we'd potentially be looking at a pH trim at the back end, or consideration of other chemicals that have less impact on pH. So the likes of sodium carbonate and bicarbonate. So we just wanted to thank our other colleagues who've been involved, Hugh, Alika, Tom and Richard. And thanks for listening. We'll try and answer any questions that you might have.
Thanks, Wendy and Caroline. Any questions? I've got a quick question, actually, which was when you switched to single-point dosing, did it create any foaming on the SAFs? I just wondered whether there's any nutrient issues around that, or did that run smoothly?
No impacts on the SAFs, actually, no.
Okay. Any other questions? No? Okay, well, thanks again, and,
Lady at the back.
Hi, sorry, Jill Smith, Wastewater. Just wondering when you went to front-end dosing, what was your iron to P ratio at that point?
Sorry, what was
sorry,
it the iron to P ratio?
Yeah, when you were front-end dosing only.
It was about 2.5.
So you remained on 2.5. You didn't increase your front-end dosing.
We didn't. No, we didn't need to increase.
Okay,
that.
thank you.
Yeah.
Okay, well, one last question just here.
Hi, yeah, Peter Pearce at Farmer Fisher. Just a question around the alkalinity dosing again. What effluent alkalinity were you targeting? What's your standard? What's the minimum that you need to require these days?
Yeah, we were targeting 50 milligrams per litre, which is the United Utilities requirement. And it was with the 2-point ferric dosing, it was a struggle to get there. It certainly was.
And the alkalinity dosing is there predominantly to maintain nitrification. So were you able to do that? Did you see the beneficial impact on nitrification, or did you see any problems with that?
No, there was sufficient for the nitrification. We were always in excess. I think 30 milligrams per litre was the lowest we got to. So I think, in terms of process, we were absolutely fine. It was just really trying to meet that asset standard that we were obliged to meet.
Thank you.
Yeah.
Okay, right. Thanks again.
Thank you. Thanks.
Okay, so move on to our last speaker for the morning before lunch is Julie Jevons and Martin Jolly talking about Yorkshire Water's BIOP schemes.
Right, it's down there. Oh yeah. Good afternoon. Yes, good afternoon, everybody. So I'm Martin Jolly. I'm from Yorkshire Water. I'm engineering manager at Yorkshire Water, and we're going to talk about enhanced biological phosphorus removal in Yorkshire. So Yorkshire Water previously doesn't have many works with phosphorus consents, and in AMP7 a large part of Yorkshire has now got a lot of phosphorus consents. So it's a big change for us, AMP7. A huge part of Yorkshire has now got to achieve new consents. We've got 741 kilometres of river to improve, and we've looked at this, and you can see the numbers on there: 16 drivers, 930 obligations, and 40% of our sewage works getting new consents, 80 sites with phosphorus consent. So that's the YNET programme, and also on top of that we need to make 30% embodied carbon savings on the business plan. So a few statements there. I mean, our approach is to look at the catchment, see whether we can balance the consents across the catchment so that we've got the best investment scenario, with potentially increasing some of the consents for the small works and decreasing for the large works, so we get the same amount of phosphorus in the river, but we spend the money in the best way across the programme. And we were determined that we would look at alternatives to chemical dosing as a strategy. We then have employed Stantec as our strategic planning partner, and we're looking at a TOTEX hierarchy, which I think Narinda showed previously, where we look to look at the problem in terms of resolving it without spending money, optimising the works, and then looking at building less as the hierarchy. And we've put in place a new process of the way we analyse our solutions within a new end-to-end process, which we didn't have previously. So if we just go on to the actual scale of the challenge. So we are looking at converting 14 of our biggest sites. So it's all the big works in Yorkshire, which equates to 3.1 million PE. So that's about 3/4 of all the sewage in Yorkshire is looking to be converted to biological phosphorus removal. Now, that was our strategy. We believe that that's the lower carbon method. We then wanted to judge that on the TOTEX solution. So that's the combination of how much it's going to cost us for capital spend, and then what is the OPEX over a period of 40 years. So we have judged every single time on whether we're meeting that challenge. So we've got 14 works, we've gone through each of those 14 works, and we've worked out which ones have got the best TOTEX solution, and we've also looked at the carbon on those as well. So how do we do that then? So the works were subject to quite a lot of sampling, and then also computer modelling using BioWin. Stantec have done a lot of work on that, and we've got conclusions there which Julie will go through. And what we've just generally said is we will take the existing works and we will modify what we've got. So we're trying not to build too much extra. There are cases where obviously that we will be building extra, but with the principle is that we're going to modify our existing works. So that's a list of the works. So you'll see there that generally they're all pretty big. Number 10 Nostrop is our biggest works, that's Leeds. And then you've got Blackburn Meadows, which is number 2, that's 460,000 pop, that's Sheffield. So you've got, and then number 7, 367, that's Bradford. So all the big works in Yorkshire are having a look at that. And then you see on the chart there, that's sort of a map, and you'll see the numbers: Bradford 0.5, Nostrop 0.4, Halifax 0.3, etc. looks like at the bottom there, Old Whittington 0.25, that's like the lowest one we've got. So, yeah, just going through again what we're thinking, we're looking at judging everything on TOTEX. We don't want to be reliant on chemicals, and we want to build less. So what I'll do is I'll hand over to Julie for the detail. There you go.
So when we started the process, we had 20 sites in total. And what we set up was a dedicated team to look at the EBPR projects. And then in parallel to that, there was another group that was looking at the low carbon initiative across the whole of the YNET programme. And that covered the catchment elements that Martin mentioned. For the 20 sites, there was a desktop comparison of EBPR against chemical dosing. And they were costed for key meeting 1. At the end of that phase, which is now complete, the 14 sites that Martin's just talked about were taken forward for EBPR. So there were 6 sites that dropped out because it wasn't cost effective to go into the EBPR route. So they went forward as chemical dosing. Phase 2, well, COVID hit. So the sampling programme that was done was interrupted slightly, and the teams faced a considerable challenge in not being able to get out onto site and look at the assets. But we ploughed ahead, carried on, making best engineering judgments with the information that we had available. And that modelling went forward. And from phase 2, 11 sites went forward as EBPR, another 3 dropped out and went to chemical. We're now going through the outline design phase, looking at working with the contractors. So we talked, if anybody was in the session earlier with Amber, she talked about some of the collaboration that collaborative approach we've been using with the contractors, etc. We looked at all of those, working with operations as well, to make sure that they're happy with the solutions, because operating an EBPR plant is a lot more complex than trying to operate an ordinary ASP. That phase 3, we're still going through that, and so far 3 plants have gone through and have had outline design complete and in the process of being handed over to the contractors. 1 of them is still EBPR, 2 is still chemical, but we're still working on the other sites as chemical. So I just wanted to talk a little bit about some of the low carbon initiatives that we've looked at. This was balancing the permits. So for all of these, the objective is to maintain or improve the environmental objectives, but to actually do that in such a way that we have a more relaxed permit to meet at certain sites. Some sites might have a tighter permit. And with the Huddersfield complex, that gave us quite a good win because the permit was relaxed from 0.25 to 0.5. And that means that rather than having to build a TSR for the full stream, we're refurbishing a sand filter. So there's a considerable capital and operational saving there from not having to build an additional tertiary solids plant. That plant has actually gone through to chemical as well. It was the nature of the waste. There's a high trade component, so it wasn't suitable for EBPR, and that has gone forward as a chemical solution. Another low carbon initiative was Halifax. Again, if you were in Amber's presentation earlier in the other session, she talks about the SIL assessment. Well, when we looked at Halifax in detail and did the SIL assessment, it was already meeting the permit. So it's actually performing 0.11 milligram per litre. That's currently being monitored in more depth just to make sure that we've got a robust solution But again, that's looking as though it will go forward with minimal investment. Now I just wanted to talk about a little bit about innovation. Now, when we think of innovation, there's a tendency to go for the nice, new, shiny, latest technology. But innovation's a lot bigger than that. It's about the way we work, what processes we use, how we deliver. And it's any new idea that we can bring to bear. So at Nostrop, this was a site where there was a lot of headroom in the existing activated sludge plants. They're currently operating with 2 lanes out of service. So the solution here was to actually remove the surface aerators from ASP1, which you'll see in the bottom corner, the blue box, and to turn that in, repurpose that as an anoxic tank to denitrify the RAS. So the capital spend here has been dramatically reduced. We're building 1 new RAS anoxic tank for ASP3, but ASP2 will be served by a repurposed ASP1. So we're removing that inefficient aeration and reducing the capital spend on the plant. Now, a nice shiny new technology. We did a quite extensive assessment of all the different technologies that are available for tertiary removal across where we needed them on the sites. The ballasted settlement technologies really come into their own at these larger sites with the tighter permits. And the decision to go forward with this technology for Blackburn Meadows at Nostrop, which are 2 of the largest sites, that was based on a visit to the COMAG installation at Finham. So hopefully, if you're interested in that, listen to Susie's presentation this afternoon. So is everyone aware of what COMAG is, or does anybody need a quick explanation? No show of hands, so I'll assume you're all okay with that one. One of the biggest challenges with EBPR is how to deal with the sludge liquors. The phosphorus that's released in the returns that need to go back to the plant. Across the programme, we're using a mixture of ferric dosing, adding lime to the sludge, because that increases the pH and precipitates out the phosphorus. But at Esholt, Yorkshire Water made that decision to try to install the Elevac P technology. It's not the cheapest capital, but on a whole life cost assessment, it's got the lowest whole life cost. And this works on the principle of adding magnesium oxide, using a vacuum to draw the CO2 out of the sludge. That raises the pH, and the struvite that would normally have formed in the liquor returns lines, that's actually precipitates within the sludge. So you're removing the phosphorus from, you're binding the phosphorus into the sludge, so that then when it's dewatered, the liquor that goes back to the plant is low phosphorus and doesn't put that additional load back onto the plant. The other thing that we're doing, as Amber talked about this morning, is real-time control. So EBPR is more complex than an activated sludge plant. It takes more operation, needs more looking after, and having that real-time control to actually help control the recycles, ensure that you have the anaerobic conditions in the anaerobic zone, that you have really good control on the oxygen to make sure that you can denitrify properly, minimise the nitrous oxide emissions, but really try and get the system stable. because a stable EBPR process means that for those sites where we need some tertiary solids removal, we can minimise and reduce the chemical dosing. And if anything's taught us, if we've learnt anything recently about chemical supplies and fuel, etc., then the less chemical we use, the more robust and resilient and secure delivery of these phosphorus permits is going to be. So the key lessons that I wanted to bring out really were how to make a successful EBPR strategy, because the conversations that I have tend to be around, well, chemical always comes out more with a lower cost. We want to be more sustainable, but EBPR is not affordable, is it? And what we'd done is we'd learnt really from what Severn Trent had done with the way that they make the best out of the assets that they've got to get the EBPR to work as well as it can, and then top up with the chemical. But for anyone who's actually looking at EBPR as an option, the most important thing is to pick the best sites. So let's go for the larger sites. That's the one with the biggest potential to save the chemical, because you'll get that return on the capital investment. Look for the sites with some ASB headrooms, such as Nostrop, because that means you can minimise the amount of build that you've got. If you've got a site that you need to expand your ASP, that's the perfect time to look at EBPR, because you're having to build that additional capacity at that time. The traders that are in the catchment and the wastewater characterisation, that's really, really important as well, because if you've got the right traders, you've got the right waste, you don't need to do any fermentation. So it's the traders, the food manufacturers, the Coca-Colas of this world, and the breweries. Those are the sites, those are the wastes that will give you the site with the best chance of success. The chemical wastes, they tend to be not to be so good. And then the other challenge is a site where if you're already thickening SAS separately to the primary sludge, then that means there's less investment on the sludge route. If you've got a site where you're co-settling or co-mixing SAS and primary, and you've got to try and separate those are going to be a more of a challenge from a CapEx perspective, because as soon as you put the SAS and the primary together, that's it. All the hard work that's been achieved getting the phosphorus into those bacteria, it's all going to be returned back into the process. But the most important thing really is actually having that strategic commitment at board level. A lot of the challenges that I'm sure everybody in this room is aware of is the idea that you need that payback for investment within a 5-year AMP cycle. You need to look behind, it needs to be viewed beyond a single AMP. Having that net carbon zero commitment is important as well. The whole ethos of sustainability, wanting to actually achieve that sustainable outcomes, that has to come from the water company's board level, because individual engineers working on projects, you can come up with the best technical solution, but there's it needs the commitment that it's not all about capital cost. It's about putting in the best solution for the environment and for our customers. So go back to that first slide, or one of the early slides rather, about how well have we done. We've got the lowest TOTEX because we've picked the right sites. Any site that didn't give us the lowest TOTEX, that's gone to a chemical solution or will go to a chemical solution. We have reduced the reliance on chemical. Current estimates, we're looking at saving 10,600 over 10,600 tonnes per annum of ferric and over 50,950 tonnes of sodium hydroxide. because of course the other advantage of all that denitrification is that alkalinity payback, so it really cuts down on the alkalinity dosing costs. And sadly, all Yorkshire Water sites are in the area where it's got the softest water. So if they were all chemical solutions, there'd be a lot of caustic going in. In terms of building less, we've got a 25% saving on the business plan for CapEx, and 5,000 tonnes of carbon saving. That's embedded carbon. The current estimate is about 11,000 tonnes per annum as an operational saving. Finally, I'd like to acknowledge all the hard work and dedication of our global team that have contributed to this programme. We've got people there from Pune, Leeds, we've got Yorkshire, we've got people from Denver, Colorado, and Canada. So it's been a truly global effort to bring a sustainable future for Yorkshire Water. Any questions?
Thanks, Julie and Martin. Excellent talk. Got a couple of questions that are coming in. First one's from AJ Nair, and he asks, with regards to the embodied carbon, what consideration was made to nitrous oxide emissions due to the changes you're making to the ASP plants?
We've got a separate project with Yorkshire Water looking at that, looking at process emissions. What we will be doing is, as I said, installing the RTC, the real-time control, to make sure that dissolved oxygen is maintained in advance so that we've got full nitrification, and just trying to reduce, just trying to control the process as well as best we can. I'm sure as technologies develop and our knowledge improves on process emissions, then that can be built into the process. But at the moment, we have to push forward and do the best we can with the knowledge and the technologies that we have to hand.
Okay, thanks. And another question here from Matt Smythe. He asks, so that quite a few sites in the UK receive large quantities of iron-rich water treatment sludges in imports or kind of down the sewer. Would they interrupt the EBPR process?
The sites that we're looking at, a number of them do have quite a bit of water treatment work sludge going in. So that is, you can see it. You've got a really low ortho P really low ortho P compared to your total phosphorus. So we are seeing that on these sites. So that's been included in the modelling. There's been allowance made for that. I think it's the consistency of that discharge. So it is a risk in terms of what's going to happen to that sludge in the future. Do we need to look at that in terms of actually try and control the way that's discharged so that it's a more regular supply and it's not, so that we don't get a big variation in the orthophosphorus going into the sites. So that is another, that's on the risk register. There's a list of them.
Okay, thanks. Any other questions? I think everybody's thinking about lunchtime. Oh, well, okay, one last question over there. Thanks.
Hi, Julie. Carl Cusack from Severn Trent Water. My question's just about the biowind modelling and how much weight you're putting on that, proving, in a sense, that BioP will work versus the more basic ratios of cod to P and so on.
We've got limitations, obviously, on the biowind modelling because part of it is to do with the amount of sampling that you can do, the amount of calibration and verification that you can do on the models. The sites with the tighter phosphorus permits, we have got chemical dosing and tertiary treatment on the back end. We've done stress testing on the biowind models to say, well, what happens if the water treatment work sludge goes away, for instance, and we get the higher ortho P? What happens if the traders disappear? What happens if we have a really extended storm in the middle of winter for quite a long time? And it rains a lot in Yorkshire. I'm quite, it's quite dilute and quite high flows. So we've done all of that testing, and we think we've got most of the scenarios covered. We've taken the approach of, we need to make sure we meet the ammonia permits. We've sized everything to make sure that, if something goes wrong, we can add a little bit more chemical. But there's also other options around, we could try and, have mitigations around improving fermentation in the primary tanks, that sort of thing. So, yeah, there are risks, but we think we're managing them, and we've got it under control, that we've got a fairly good handle, because we've modelled the hell out of it.
Thanks, Julie. So, it's been some great questions. Hopefully we can carry on the discussion over lunch. So I'll just finish off by thanking all of our speakers, and thanks once again, and cheers.
Hopefully we're all fine and raring to go after lunch again. Welcome to the afternoon session, which is on phosphorus as well. My name's Michael Froome. I'm Business Development Director for T-Tech Process Solutions, so I'm your chair for the afternoon. I think we have one session through till drinks at about 3:15, and Francis has asked me to mention that there's a drinks reception in the exhibition area between about 5 and 6 this evening. We'll start the afternoon session with Susie Vale from Severn Trent Water. Thank you.
Good afternoon. So today I'm going to talk about the COMAG process at Finham, which is the largest COMAG installation supplied by Wastewater. Okay, so my talk will take the following format. I'll start with a brief overview of COMAG, what the process is, a bit more detail about the Finham installation in particular, look at some of the plant performance, before talking a bit about the lessons we learned when we were commissioning the plant, and then finish with a few conclusions. So, COMAG is a ballasted coagulation process, a settlement process, which uses magnetite to weigh the flock down. At Finham, we use it as a tertiary process for the removal of phosphorus. So the first stage, we dose ferric sulfate, and this is to precipitate out the phosphorus from solution. Coagulation then occurs in the first of two reaction tanks here. The flow then goes into a third reaction tank where magnetite is added, and this is embeds in the flock to ballast it and weigh it down. There's three sources of magnetite. The first is with the recycle from the bottom of the clarifiers. The recycle is typically 5 to 10% of the inflow. The second is the magnetite which is recovered in the sludge, which is returned back into reactor tank 3 as well. And then the third source is virgin magnetite, which is added, and this is just to top up the losses from the system. In the fourth reaction tank, we add polymer. This binds up the small flock into bigger flocks so they can be removed. And then the mixture goes into clarifiers. This is where the final effluent is settled. The solids are settled, so the final effluent can be separated from the flow. The solids settle at the bottom of the reactor, and then you've got the recycle going back round. I always think the recycle is a bit analogous to the RAS in an activated sludge plant, but Evoca will probably won't like this description. It's a solid separation process, so we have to move the solids from the system. So 20 to 30 minutes every hour, the sludge recycle pumps operate, and they send the sludge through to the magnetite recovery. So the sludge magnetite mixture goes into the recovery system. This consists of two different stages. Firstly, the shear mixer. I've got a bit missing on that, okay. So this is the shear mixer, and this breaks the flock up and releases the magnetite from the flock. The sludge then goes into the magnetite recovery drum, where the magnetite is removed from the sludge. The magnetite drum, or mag drum, consists of an array of fixed permanent magnets, and round this there's a steel drum which rotates. The magnets, which will be here, attract the magnetite to the surface of the drum so they can be removed. So this is Finham. I'll just describe how it was before we installed the COMAG. Very briefly, it has two inlets, the Sherborne inlet and the Sow inlet. Each has screening grip removal. There's two sets of PSTs, the north and the south. Each have 3 PSTs. Then moves into, it was an activated sludge plant. It's now been converted to IFAS. So there's 3 activated sludge plants. Each has 4 lanes and 4 final settlement tanks. So there's 12 final settlement tanks in total and 12 lanes. We used to dose ferrous sulfate. We had a 1 milligram per litre phosphorus permit. And then on the back end, there was also a tertiary solids removal, a sand filter, which hadn't been used since the 1980s. So a few figures about Finham. Finham's one of our larger works. It has a population of just under 500,000. Has a FFT of just over 2,500 litres per second. So when the permit was tightened from 1 milligram per litre to 0.2 milligram per litre, it decided that the COMAG process would be installed, and this won on whole life costs. One reason was that the COMAG plant could be retrofitted partly into the existing sand filters. So the final effluent from the final settlement tanks gets pumped up to the inlet of the COMAG plant, where there's a channel static mixer. So the channel static mixer and the 4 reaction tanks are fit into the existing sand filter. Then it goes into, we have 2 clarifiers. The clarifiers were both designed to treat 75% of the maximum flow, so this gave us some process security when we took one out of service. So this is a photo of before and after the installation. So this photo here, you can see the sand filters, the 6 cells. We had old humus tanks here, and we installed the COMAG in the first and the 6 of the sand filters. So there was the inline channel mixer, and then we had the reaction tanks afterwards. We also used the base of the humus tanks to install the high rate clarifiers here. Just to put it in perspective, these are the existing final tanks. So there's 12 30.5 metre diameter final tanks. And they treat the same flow as the 2 COMAG clarifiers here, which are 21 metre diameter. The reason they can treat the same flow is that they operate at a lot higher upflow velocity. So the final tanks typically operate at about 1.2 metres per hour. Under normal conditions, the COMAG clarifiers operate at 14.9. But when one's taken out of service, the upflow goes up to about 22. So looking at plant performance, the COMAG has performed very well. So looking at the ortho and total P, on average, the influent total P was about 0.7, and coming out was about 0.1. The iron, the 95 percentile going in was at 0.7, and this went up to about 1 milligram per litre. Magnetite's about 72% iron. It's an important thing to note is that any magnetite in the final effluent doesn't get picked up in these iron results because it doesn't get picked up in the analytical method at the labs. Suspended solids, 95 percentile was about 13.2 going in and 12.2 going out. This graph just shows you the total influent and effluent total P, and also the reactor, the concentration of magnetite in the last reactor. The design was about 6 to 8 grams per litre of magnetite. We struggled to get this from the start of commissioning, and the levels reduced for reasons I'll go into in a bit later. They did actually drop to about 1 gram per litre, and we had to start capping the flows. So comparing the actual magnetite consumption to the design, the first thing we noticed was that the initial prime of magnetite to prime the system was about 3 times greater than we envisaged. This was due to the magnetite settling out in quiescent areas of the process, in the reaction tanks and in the clarifiers. There was quite a gap below the scrapers in the clarifiers, and the magnetite settled out there. As the plant was operated, the actual consumption ongoing was also greater than we thought. One thing to note is that the quoted recovery rates across the mag drum, they're quoted at average flow, so when the flow goes up, the recovery rate goes down. So there was loss there. But the main loss we found was going over the final effluent weirs. So how did we know it was going over the final effluent weirs? Well, firstly, we could see it. It was also getting stuck in all our final effluent monitors. both had magnets, and we've got an ozone plant downstream which feeds the golf course, and it's getting trapped on top of the lamps, and it was settling out in the channels. It's quite hard to actually measure it, so just taking a sample wasn't very representative, so we formulated a new way of sampling it, taking a known volume of effluent, putting it through a domestic magnet filter, and separating the magnetite out, which seemed to work quite well. So we noticed that the loss of magnetite worsened after the performance tests, so we needed to find out what was causing this. There's several changes which happened since the performance tests. We decreased the polymer and ferric sort of optimization, and it also changed the type of polymer because we had a change in the supplier of polymer. So in order to ascertain what the cause of the increased loss across the final effluent weirs was, we had to revert back to the original settings for everything. We changed one at a time and then monitored performance each time. So the performance was monitored by turbidity in the effluent, by visual, seeing how much went over the weirs, and then also how much we had to top up the system. It was quite hard to sort of see the impact of each change because the flows were always different from one day to the other, and we also had to cap the flows to reduce the loss of magnetite. But finally, we decided that the main cause of this loss was the polymer. So now we've reverted back to the original polymer, ZTAG 54110, and performance has improved. But the issue with the polymer did highlight an underlying problem. So we noticed that the loss of magnetite was worse in the segments of the clarifier which were perpendicular to the inlet pipe. So they were worse over these sides, which immediately drew attention to the inlet arrangement of the inlet pipe to the clarifiers. So as you can see here, there was a baffle placed opposite the influent pipe. The idea was this, to dissipate the energy before it hit. There's a concrete column in the middle of the tanks. But what was happening, we got CFD modelling done, and it showed that the baffle was pushing the flow down, it was scouring the solids off the bottom of the tank and pushing them up over the weirs. And that was what was causing the loss over the final effluent weirs. So we now need to do some modifications to that inlet pipe work and that inlet baffle, but progress is still ongoing. So we haven't got the final solution yet, but it'll be, whatever solution it is, it'll be CFD modelled first. A few other things we noticed. When we first commissioned the COMAG plant, we had to switch it off over Christmas because we weren't confident of leaving it running over Christmas. And when it was brought back online, everything turned black. The sludge had gone septic in the bottom of the clarifier, and because you've got the recycle, it's just turned all the reaction tanks black and the whole system. In the end, we had to drain everything down and fill it up with final effluent. So now we have a sweetening flow, which comes on when the clarifier is offline for more than 3 to 4 days, just to keep it sweet. And that's an automatic control. Another thing to consider when you're doing the design, the mixers are essential for the design, especially the mixers in reaction tanks 3 and 4, where the magnetite's added and the poly. If you lose a mixer, if you don't have sufficient standby capacity, you'll lose your process. And as I mentioned a bit ago, you need to note that iron associated with magnetite is not included in your iron results, but it does get picked up in your suspended solids results. So just to draw a few conclusions, the COMAG plant works very well, and it meets its total permit of 0.22 milligram per litre and 95 percentile iron of 4 milligram per litre. The inlet arrangement to the clarifiers is essential for the success of a scheme, and also the polymer section. The magnetite consumption was higher than expected at Finham. I think we're beginning to understand why. Although our second COMAG plant, which is at Cannock, that seems to be, the consumption of magnetite seems to be to design, so we don't seem to be seeing the same issues there as we have at Finham. So if you've got any questions, far away.
Thank you, Susie. There aren't any questions on hopping at the moment from the virtual audience, or if you'd rather put a question on there yourself, then feel free. Duncan.
Mm.
Have you done any tests with any other methods to understand what it might be? What's the other method that can pick it up regularly?
So that's the lab standard method. We have tried to measure it ourselves, so as the suspended solids, and then have the percentage of iron in that. I think the suspended solids is about 2.26, I think, milligram per litre, and then 72% of that would be, so 1-2 milligram per litre.
Question at the front.
Hi. Thanks very much, Susie. It's very interesting.
Sorry.
I just wondered whether you found a solution to the diffuser, to the
baffle plate.
The baffle plate.
We haven't at the moment. So it's relatively recently, when we've done the CFD modelling, we have had it modelled just putting holes in the existing baffle plate to see if that improved it, but it didn't significantly. So the next step is to put some proposals together and get them modelled. So no, we haven't at the moment. I believe there's a different design at Cannock. They've got a different inlet arrangement. But I think it's going to be quite hard to retrofit that one to our tanks. So.
Thanks. Pete Pearce here. Sorry, Formula Fisher. Carrying on, really, a question on the clarifiers. Presumably they're not your design clarifiers. These were designed by the supplier, is that right?
They were, yes. I think they're it's designed, I think there's States designed. I think the Evoque probably, they were in. Do you want to answer this one? About the clarifier design? No, this was their design.
I think we're putting Simon on the spot.
Sorry.
Sorry, what was the question, Pete?
So just with regard to the clarifier design, obviously they designed at very high upflow rates, which is presumably part of the normal process design. It was mentioned they were built on existing bases, but presumably the rest of it is your design. I'm just wondering whether you had come across this problem before. You must have put a lot of these installations in, but just what your comments were really on it.
Yeah, I think the most important part of it is that we tend to emphasise on the negatives in terms of there is a magnetite loss. However, as Susie said, you're getting a really good performance out of the process. So that's the most important part. But yeah, there is some improvements, I think, that could be made with the clarifier design, which we've implemented in later schemes. Correct. Yes.
Yeah.
Thank you, Simon. Any other questions? Probably got time for one more. Just in the middle of the room there.
Hi Susie,
Hi,
Jeff Gibbs with Elecor Hydrock. I'm interested, how long does it take to start it up and shut it down?
I think it's relatively quick. Again, Evoque, I haven't been involved in the direct commissioning of it, so, but yeah, I think it's pretty quick.
When you say quick, is that minutes or hours?
Yeah. Thanks, Jim.
Any further questions? If not, Ron, done. Yep.
5 to 10% of the feed flow-ish. Sorry? Of the, I think the current flow, yeah.
Okay. I think we'll
Thank you.
draw a close there. Thank you very much, Susie. And the second presentation, still dealing with the COMAG process, from Wastewater, Dirk Emery Wastewater, from Victoria Wilson, Harrison Brown, and Daniel Corse. Again, if you want to put questions on Hopin, if you're logged in the room as the presentation goes on, feel free, and equally from the virtual attendants.
Well, nice to see everyone in person. It's obviously been quite a while, but today's presentation is going to be on the COMAG process that's recently been applied at 2 Welsh water sites, namely Letty Brongu and Riffin. So I'm Harrison Brown and I'm from Avocqua. So what is COMAG and how is it applied? Well, we've just had a really good presentation from Susie who's explained all the details of it, so I won't spend too much time now just kind of going through it, but I will just give you kind of just the highlights, I guess. So there's essentially 3 chemicals that we're adding as part of our process in a series of 4 reaction tanks. The first being a ferric coagulant, the second being a magnetite, which is a ballast, and the third being a polymer, which is a flocculant aid. We also have an underflow from our clarifier, which is continuously feeding at a rate of, like we said before, 5 to 10%, and that's essentially recirculating that magnetite back into the tanks, and that also enables us to reduce our ferric usage. So, magnetite. Why do we use magnetite? What makes it so special? Well, the first thing to note is magnetite's used in a wide variety of applications and it's available from multiple number of sources, which is obviously really important when we don't want to be streamlined from the same supplier for something that we're going to be using as a daily top-up. But if we actually look at the substance itself, we can see it's got 5 really compelling properties which make it an ideal ballast. So firstly, it's completely inert. As we know in wastewater, we get a lot of contaminants in there, and it's really important that anything we do add into our system isn't going to react with anything, so that's why magnetite's really good from that respect. Next, and probably the most important aspect of a ballast, it's really heavy. Obviously, if it's going to be ballasting, you're trying to weigh your flux down, you want it to settle quickly. The most important thing is it's really heavy. With that said, it might be really heavy, but it's going to be no good if it doesn't actually embed into your flux. So magnetite, it's got hydrophobic tendencies, and you can see on the bottom left there, that's a microscopic image, which basically is showing the magnetite embedded into your flux. Next is magnetically retrievable. It's no good having this ballast if we're just going to be wasting it in the waste sludge every time, so we need a method of getting it out. Magnetite, as the name suggests, is magnetic, and we can use that to our advantage to remove it using something called a magnetic recovery drum. And finally, and probably the most important to a lot of people, it's very inexpensive. And that's largely due to the facts that I said before, and the fact that it comes from multiple number of sources, so that kind of helps keep the prices down of it. So, Letty and Riffin. If we actually have a look at the 2 sites and just give a bit of a brief overview. So Riffin is located in the north of Wales in a really rural area, and Letty Brongu is a bit of the opposite. It's located in the south of Wales, in between Cardiff and Swansea, and it's quite a population-dense area. So we can see the layouts of the sites there, and they look really similar. In fact, they're actually more than really similar, they're exactly the same. So they're both using primary clarifiers, followed by trickling filters, and then finally humus tanks. So I'll go on the next couple of slides on how we actually apply a COMAG to a trickling filter site rather than an out-and-out tertiary, but just for now I just want to give you a bit of an image of what the COMAG system actually looks like on both of these sites. So it might look on first glance that Riffin is different, but actually that's not the case. With Riffin being a lot smaller a site, the 4 tanks have been integrated into a single unit, which is why it looks like 1 tank on that picture. And Letty, you can see there's 4 distinct tanks. And lastly, there's just a little bit of a video which I'll just quickly walk you through, which shows the COMAG process actually in operation at Letty. Oops. I don't think we'll have a video, but that's fine. We'll explain it on the next slide. So if we actually look at the sites by numbers, I'm not going to bore you with numbers. There's a lot of numbers on there. I'm not going to go through all that, but I'll just point out some key ones. So the design basis that we had to meet for Letty was phosphorus of 0.5 milligrams a litre or less, and at Riffin 0.25 milligrams a litre or less. And whilst achieving this, we also had to meet our iron content, which on both sites was 4 milligrams a litre. The other really important number to note on this slide is the total solids that's coming into the COMAG. So you can see at Riffin, for example, the average is 45 milligrams a litre and the 95th percentile is 75 milligrams a litre. Obviously, this is something that's really high for an out-and-out tertiary to deal with, which is where the COMAG really comes into its own, and it is really able to deal with these high solids loads, which make it a great option for a trickling filter site. So how exactly is COMAG applied on a trickling filter site? Well, it's really quite a simple concept. Essentially what we're doing is we're intercepting the effluent from the trickling filters, we're feeding it into our 4 reaction tanks like I mentioned before, and then from there we're feeding it into the existing humus tanks and using them basically now as clarifiers, which have been slightly redesigned in terms of the scrapers and the inlets. The underflow from the clarifiers, like I said, will continuously recirculate that magnetite back into your tanks, and you've got this loop of magnetite going round and around. So, magnetite usage at Letty and Riffin. So, as Susie mentioned before, we have, when we first get into site and we do our process commissioning, we have something called, it's a one-off initial fill. And what that is essentially doing is it's loading your system with magnetite, it's loading it with that ballast so that it's got enough ballast basically to treat the incoming solids. So before the project, we'll use some spreadsheets to work out exactly how much that initial fill should be roughly. And you can see at Riffin to be 600 kilograms and at Letty 1600 kilograms. We actually found on both of these sites it was quite significantly less than this. At Riffin it was 400 kilograms and at Letty it was 1,000 kilograms. This is obviously a really big bonus because it meant we could commission it in a shorter time, and it also meant we were using less magnetite. But there's also a secondary use of magnetite on a site, which is the magnetite top-up. So the magnetite recovery drum, which is what we feed our waste sludge through to recover the magnetite, is not 100% efficient. There is a few inefficiencies in there. So based on that, we come up with this top-up value. And again, we see similar trends to the initial fill in that the fact that at Riffin it was meant to be 6 kilograms and at Letty it was meant to be 18 kilograms. In actual fact, this was pretty much on the money. You see on there the reason it's slightly higher than what we actually predicted was just to make it easy for the operators. With bags coming in 20 kilogram intervals, this essentially meant at Riffin they could do 1 bag every 3 days and at Letty a bag every day rather than weighing out awkward quantities. But how exactly do operators know how much magnetite to put in? Because over time it could potentially change. So it's a really, really easy principle. So effectively, during process commissioning, we'll give them a target magnetite concentration which they should be aiming for. Once or twice a week, the operators will take a sample from tank 3 and tank 4, they'll place it into the mag meter, which you can see on your screen there, and they'll simply press that blue button, and on the interface it will read out a concentration. So magnetite management really is a very straightforward procedure, and it's really made easy by this simple mag meter device. I'll now pass you on to Dan Course from WSP, who was the process engineer who was commissioning it at M&B at the time.
Thanks, Harry. So yeah, as Harry explained, I was the process commissioning engineer from MMB, and I'm just going to go through very briefly about the design, integration and commissioning of the COMAG plant at Cletty Brongy. So just a bit on design to begin with. We had a very high water table down at Cletty. So as you can see on the picture on the left, everything is, well, pretty much everything is DFMA. Water site and kiosk put onto slabs, including the 4 COMAG tanks in the top right of the screen, which really shortened down the construction program. Collaborative planning is a bit of a buzzword that goes around, certainly within MMB, but it was actually really, really important to make sure we nailed that. This wasn't just between Evotca and MMB. We had to involve mechanical subcontractors, electrical subcontractors, chemical suppliers, chemical dosing suppliers, just to really make sure that we nailed the short construction program. Jar testing, again, is another thing that is, it seems quite easy, it seems quite simple, but in our case, we went through 2 sets of jar testing. The first one was really just to involve process scientists, commissioning scientists from Welsh Water, just so they could see for themselves how it would, what the COMAG would look like and how the chemistry works. But also we took it as an opportunity to really nail what polymer to use, and also just to verify what chemical consumption we had in design, just to make sure it actually suited what was out on site. And finally, use of existing assets. It was quite a small capex budget on this project, so use of existing assets was quite important. So integration with the existing. So one of the assets we made use of was the HSTs, which turned from 2 HSTs into 1 COMAG clarifier. So the modifications we made to that were just the scraper blades at the bottom, and the weir level was raised around the top, so we could just operate on 1 tank only. A bit of a lesson learned and a bit of an oversight here. So a COMAG clarifier is never going to meet conventional process standards for water frameworks. However, that doesn't mean you need to overlook every single aspect of it, which admittedly the diffuser column in the middle you'll notice is quite narrow. Although this didn't affect compliance and carryover, it's inevitable that you are going to get some pluming, which, to somebody's not familiar with the process, it could spook them a little bit. So it's quite important to, make sure you look at the whole clarifier. Picture in the middle on the top, it just looks like a simple T branch, but this is into the existing desludge system from the humus tanks. Again, making use of existing assets is great, but perhaps what was overlooked as well was exactly how we would tie into that system whilst maintaining compliance on site. Biofilter flow diversion, so as Harry mentioned earlier, this process intercepts the flow from the biofilters to the HSTs. So we used an existing pumping station, put new pumps in it to feed the COMAG, which is above ground, and built this new diversion manhole. Biofilter recirculation. So again, we knew that recirculation on this site was important because nighttime dry weather flow is an awful lot lower than FFT, but we didn't quite perhaps appreciate the impact that this would have during commissioning, particularly in summer months. The ferric dosing for the COMAG process operates on a fixed flow. It's flow-paced. So if you've got a high flow at night, which is primarily made of recirc, you haven't got a great phosphorus load in there, but you are putting in the same amount of iron as though you have got a high phosphorus and a high flow. HST distribution chamber mods. Again, perhaps this is something where commissioning and design weren't really talking to each other properly. You can see in the middle of that picture, there's a temporary baffle that we made just to dive, so we could completely segregate COMAG flow and biofilter flow. This was because during commissioning, the COMAG only takes 50% of FFT during that commissioning process. So the other 50% has got to go somewhere, which meant we had to keep the other tank online. So it was quite difficult during commissioning to completely segregate two systems. And finally, just a little bit on temporary treatment down there. Although temporary treatment seems quite simple during the design process, this was on site for about 12 weeks and involved over 800 metres of flanged pipework, so it was quite an operation. In terms of the actual commissioning process, with like any technology, there's 3 stages: dry commissioning, so just checking input and output modules and going through the FDS. Wet commissioning, which took about 6 weeks, and this is just operating the COMAG on water and testing the chemical dosing units, but with water only. Because this is tying into an existing system, it wasn't quite as simple as just saying, we'll do COMAG and keep the other process online. Because the COMAG ran on one clarifier, we couldn't send flow through there that hadn't been dosed with iron or polymer or magnetite just through one clarifier through final effluent compliance risks. So what we had to do was create a bit of a closed loop and just test it within a closed system before we went on to process commissioning. 2 weeks seems quite short for process commissioning, but all we're doing is just adding chemicals. We know roughly where we're aiming at for jar, because of the jar testing results. And I think the only tweaks that we made during process commissioning was just knocking down the iron dose from 8 milligrams per litre to 7 milligrams per litre, and also just making sure that the poly concentration was 0.3%. It was slightly higher during the initial stages and it caused us a few problems, but it was quite important to keep it at that 0.3%. In terms of performance, so this is just, these 3 graphs represent the first month of the COMAG coming online. Top left is total phosphorus. So the sort of 3 important lines there are the tall blue line when COMAG came online. The green line represents final effluent, total P concentration, and the red line is the consent. You'll see there's one blip towards the end of September, but that was because one of the clarifiers was offline due to a mechanical failure. But once it was brought back online, then total phosphorus compliance was met. Total iron, a little bit of an increase after COMAG was brought online, but not threatening that 4 milligram per litre consent. And finally, TSS, not too much change there, but the average is 6 milligrams per litre. And sorry, I forgot to mention, the average total phosphorus concentration in that graph is 0.246 milligrams per litre. So it really did nail it when it came online. And those pictures just illustrate the type of clarity you can get. And now I'll hand you over to Vicky.
Hi, I'm Vicky Wilson, Asset Manager for the Quality Programme for Wastewater Assets. So my team are the client for the schemes. I'm just going to talk about our process selection and then some data from site, from the samples taken by operations. So for us, we had 10 P schemes in AMP6 and 2 of them were chosen to put the COMAG in. Our process selection matrix, we use a process called the risk and value process. We look at whole life costs, we review CapEx, OpEx, we review carbon, we review complexity of the build, compliance. Obviously that gives us a benefit cost ratio, but we also look at the technology and how it's suited for the site specifics. Not every technology will apply to every site, and there are how flows presented to the site matters. So COMAG was chosen here at Ruthin and Letty Brongy by ourselves and our other stakeholders, which is operations and science. And at Ruthin in particular, we knew that we were going to get, very likely going to get a tightening P from the one that's in the NEP. So it is a new NEP of 0.5, but we asked for it to be designed to 0.25. And at Letty Brongy, we've also got the 0.5. Both sites needed not just the COMAG, we needed new chemical dosing, new ferric dosing, new alkalinity dosing, obviously the polymer to go with the COMAG, potable water, new MCC. Ruthin needed a new sludge tank, and Letty an upgrade in power. So for us, it's the wider site requirements as well. So for Letty, obviously it's our biggest one of the 10. We had a population of 21,000 there, and access was quite a key issue for us. So again, that narrowed down our viable options of what we would choose. So if I just go on to Letty's data, obviously with COVID as well, caused some delays, but we did start ferric dosing early at Letty, and as Dan went through, we did have issues with commissioning of the COMAG at Letty. There were modifications made, so you can just see that on the graph there, and then the end parts of the urban waste data just showing you how after the modifications we're now well down at 0.25. So we did have a step change from like 2.5 down to 1.5, 1.2, and then down to our 0.25. So what we needed. So going on just to the site data, the site data isn't as much as I was hoping, but they did do total phosphorus, and you can see from the data we have had some issues recently. We have highlighted in a line there on recirc issues, which has impacted our ferric dosing, so that's being dealt with. But the results overall are really good. We're averaging total P of 0.27, and our total iron, which I always like to see being presented, is 0.92, which is really low for us. So really pleased by that. Just coming on to Ruthin, urban waste data for Ruthin, again, there should be a line there. We did start ferric dosing earlier in the year, 19th of February, and then full commissioning started the back end of last year. There was a period of partial flows in between, so you can see that there's a step change down, but basically from 3.5 we're now down at about 0.25, which is where we want to be, and well below our 10 milligram per litre solids. So just to go on to the site data, more site data at Ruthin, although they sampled for ortho P, they didn't do total P, so the ortho P on the left there, we did have a problem with the polymer pump, which did switch off the ferric dosing, but that's been rectified, and you can see that we're averaging 0.07 ortho P, which is where we want to be. And on the iron again, really good, average 1.02 for Ruthin, and this is our site samples. So just to finish, lessons learned, lots of lessons learned, but we've had to summarize it down for today, otherwise we could be here for a while. So just under 4 headings, even though we emphasize training, more training to be provided to our site operators is really even more important than than what we had, and we raised it early on in the feasibility stage. It does make a big difference to trouble-free operation. Open impellers for trickling filter works. Obviously, this is both sites were trickling filter. They had closed impellers, but open impellers were needed due to the larger pieces of biomatter. Air entrapment, which I know Dan couldn't go into all the challenges of the commissioning period, but air entrapment did impact on the process. Because of large drops between the tanks and connecting to our existing works, it did cause performance issues and air getting in, which made the flocks harder to settle. But lots of different meetings and modifications happened, and we're at the best we can be. It would be nice to have the flocks as well as we know they're settled, because we did do a trial with the COMAG, but they are settling well enough. And then the last point, obviously integration and commissioning of the COMAG to the existing site is, as Dan said earlier, that collaborative plan, the importance of our key suppliers, not just Evocua, all the other suppliers actually had such an impact on the commissioning program. We had quite a challenge here at Letty, and that really does matter to the whole commissioning program. So that's lessons learned from us. So let's leave it as any questions.
Thank you very much. So, any questions?
Hi, it's Rowan Luck from Severn Trent Water. Interesting to see it applied to biofilter sites. I haven't seen it yet for COMAG. Do you think there are any positive or negative impacts of applying it to a biofilter site, thinking about sloughing or seasonal changes?
Well, obviously for us, yeah, the solids was an important part of the process guarantee and part of the process requirement, the data that was given to the supplier. And that was not just for these two sites. As I said, COMAG was one of our enhanced solids removal processes. So we've had other biofilter sites, and that one was really important for us, that they knew and understood the variability, the maximum, not just the average. If that makes any sense.
Thank you. Sorry, Peter Pearce here again. It's always clarifiers, isn't it? You were retrofitting, in this case, existing clarifiers, so presumably these had larger area available. So do you know what the maximum upflow velocity is on the design for clarifiers?
I'm not too sure what the maximum upflow velocity is for these clarifiers, but in terms of general footprint, I think you could design a clarifier 10 times smaller for an Evocua plant than you could for a conventional plant. So for this particular process, upflow velocity wasn't an issue.
Yeah, that's part of what I was getting to. So there were two clarifiers serving the plant pre in any way, so they would have been designed at 1.5 or 1.3 or something maximum. So you would have got much lower upflow velocities than we saw in the previous example at Finham. Does that cause any problems in its own right if the upflow velocity is too low, or is it all on your side or all in your favour?
No, I'd say it can't be too low, could it? Or...
In terms of upflow rates, you're absolutely right. Obviously, it's a lot less than what we've just seen at Finham, which is only a good thing. You know, it's just given the flocks even more time to settle out, so there's no disadvantage of that. We don't need that upflow time, but obviously we're being a retrofit. You know, we're not going to make the clarifier smaller, so it's just, yeah. But yeah.
Okay, probably got time for one more question, if anyone's got anything.
Matthijs Oosterhuis, Haskoning DHV. I was wondering what was the ratio of magnetite to phosphorus which is removed? How much magnetite do you use? And if it's absorbing the phosphates, can you then release it afterwards and reuse it again, or is it then a waste?
So in terms of magnetite, the magnetite is purely there for solids removal, so there's no ratio between magnetite and phosphorus. It's, you know, the ferric's what's removing your phosphorus and the magnetite's just removing the solids. So we don't lose magnetite, obviously. Well, we lose a small amount, but obviously it's in a recirculation, so we keep that. It depends on the site how much magnetite we need. You know, some sites can be half a gram a litre, some sites can be 2 grams a litre. It depends during process commissioning, but yeah, so essentially we're trying to keep a continuous magnetite concentration, which then will maintain our solids. But in terms of for phosphorus, it's just, you know, standard with ferric really. Magnetite and phosphorus don't have any correspondence, if you like.
Okay, thank you.
Okay, thank you very much. And the third presentation in this session, just before the afternoon break, is from Thomas O'Shea from Severn Trent Water.
Hi there, I'm Thomas O'Shea, one of the process engineering leads at Severn Trent, and I'm here today to go through the presentation, reliably meeting low total P permits while not breaching the metals permit. So on this slide here, just a bit of a brief summary of what I'm going to go through today, give a bit of a background of phosphorus removal within Severn Trent, then go into a bit more of the design side and go on to talk about commissioning, optimisation, and then a bit of the longer term approach once the permits are in place, and then go through a bit of detail on an example site. So to start off with, prior to AMP6, Severn Trent had a number of phosphorus permits. These tended to be laxer permits in the region of 1 or 2 milligrams a litre. And then in AMP6 and AMP7, as part of the WINEP programme, we've taken a lot more tighter phosphorus permits. So within AMP6, we took about 110 or so new or tightening phosphorus permits, with 20 or so of those below 0.5 milligrams a litre. And then the AMP7 programme is going to be roughly twice the size of this, with about 60 permits under that 0.5 milligrams a litre total P. So in the context of this presentation, where I'm talking about very low P permits, I'm sort of classing anything under 0.5 milligrams a litre total P as a very low P permit. So generally, to meet those sort of permits, we're talking about a pre-dose TSR solution with some sort of chemical dosing on site. Though the primary phosphorus removal may be biological rather than chemical, depending upon the site specifics. So where we've got these pre-dosed TSRs, we're generally going to have a higher risk of metals breakthrough, so that's something we have to consider more with these tighter phosphorus permits that we're working to. As for some of the sites with slightly laxer low P permits, so potentially the 0.3, 0.4, we've been able to meet the tight permits with a TSR but not using the upfront dosing. So that's offered advantages in terms of metals breakthrough at the back end, but it does present more reliance on the primary dose points, and that can have a detrimental impact upon nitrification if not managed properly. So for all of these low P permits, we'll generally be dosing a coagulant on site, a metal salt. So based upon the coagulant we're dosing, we'll be getting a corresponding metals permit. So if we're dosing ferric sulfate, we'll be getting an iron permit, which is generally 4 milligrams a litre with an upper tier of 8 milligrams a litre. If we're dosing aluminium sulfate or PAX, we'll end up with an aluminium permit, normally a 1 milligram a litre absolute permit. So the tightest total P permits that Severn Trent have chosen to accept have been 0.2 milligrams a litre. I know some water companies in the UK have decided to go lower. This is what we've sort of taken as our sort of lowest technically achievable limit. So you can see on here a selection of our AMP6 sites with the very tightest total P permits. And for these, we've got the corresponding iron permits. So for all but one of these, the metals permits are tighter than the sort of standard 4 milligrams a litre that we've been receiving, going down to as low as 2.5 milligrams a litre. So in addition to having to meet that really tight total P permit, you've also got a tighter metals permit to work with as well. So I'm just going to go into a bit more detail on the design of the tertiary solids removals plants, which are usually required to meet these very tight total P permits. So the first question to consider is, do we need the tertiary solids removal plant or not? When we're talking about the 0.2 milligrams a litre total P, it's going to be inevitable that you've got that tertiary solids removal plant. But some of the slightly laxer permits, getting up into the region of 0.4, 0.5, 0.6, it's entirely possible on some sites that you will be able to meet the permits without the tertiary solids removal process. So the reason for not installing a tertiary solids removal process is they've got quite high capex, they've got ongoing opex, and also you've got the impacts of the TSR backwash and the impact of that upon the secondary treatment process you need to consider. So if there is a chance that you can meet your total P permits without that tertiary solids removal, it's definitely something to consider. Then going on a bit to the sites where we do install the TSR, so for the sites of less than 0.5 milligrams a litre total P, when we're putting in that TSR, we will be sizing it to treat all the flows coming onto it. So usually be FFT plus your general site returns plus the maximum instantaneous TSR backwash to make sure all the flows that that TSR is presented with are going to get treated by that tertiary solids removal process. Through trialling numbers of different TSR technologies, we found that not all are compatible with upfront dosing. The ones that aren't compatible might have catastrophic blinding, leading to flows not being able to get through the process, or having a large amount of metals break through into the final effluent, neither of which are particularly desirable. So when we're designing these plants for a pre-TSR dose, we'll generally design to have a dose rate of up to 15 milligrams a litre metal as iron. We've seen that this covers most plants in terms of the maximum dose rate we go up to, though on some sites we have had to dose slightly higher than metals concentrations than this to get to the desired total P permit. Just going into a bit more detail on the TSR design itself. So the way we work within Severn Trent is we put together a data sheet which goes out to the suppliers and they undertake the sizing of the TSR units in detail, and our contractors determine what's best on whole life cost. But we are providing the information in terms of the influent solids, influent hydraulics loadings, and generally what we require in the effluent in terms of solids. So what we found for most of the pre-dose TSR installations is that they're predominantly sized upon the solids loading onto the unit. So getting that solids loading right has a big impact upon the performance of the tertiary solids removal unit. So the way we determine the maximum solids loading onto the unit is we go for the higher of the average influent solids at maximum flow or the 98th percentile influent solids at average flow. So we haven't gone for maximum solids at maximum flow, as we don't believe that's going to occur. And for the majority of installations we put in, we found this to be the case, though there are some exceptions where you do experience the higher solids loadings at higher flows. So for the TSR processes where the supplier isn't guaranteeing the effluent total P and the effluent metals, we put together a requirement in terms of what we expect on the average and 95th percentile solids in the effluent. And to do this, we have baseline assumptions in terms of the amount of phosphorus and iron in the solids. There's some general numbers given there, but it does vary on a site-by-site basis. And as we install and commission more pre-dose TSR installations, we're able to confirm these numbers further. Just touching on the types of TSR a bit. So We have a number of different types of TSR that we view as viable with upfront dosing, including mixed media filters, continuous operating upflow filters, ballasted coagulation and cloth filters. For all of these, provided that we've designed everything correctly and commissioned them correctly, we've been able to meet our very tight total phosphorus permits and still be compliant with the metals permits as well. Just want to touch on backwashing a bit as well, because this is something that, if we get wrong, has quite a big impact. So for all of these processes we're talking about, we've got a fair backwash volume that needs to be dealt with. So when we're returning that back to the head of the works, some instances we've not accounted for the full amount of returns and have returns pumping stations overwhelmed, which then in turn inhibits the TSR backwashing, which then detrimentally affects your TSR performance in terms of phosphorus and iron. And also on some sites we've not provided sufficient balancing. So for the TSR processes potentially that operate with batch backwashing, where we haven't provided sufficient balancing, we've had large flows going back to the head of the works and overwhelming secondary treatment. So making sure that you've balanced your TSR backwash volumes and considered it properly in your secondary processes is key. So as I said, for most of these very tight permits, you're talking about chemical dosing. So for the dosing rigs we install, they're generally ferric sulfate, but we design the rigs so we can change to different coagulants in future if required. And again, for the pre-TSR dosing, it's been discussed a bit today that mixing and flocculation, getting that right pre-TSR is key. So for the pre-dose TSR installations, we'll generally be dosing into a static mixer to make sure that chemical's fully dispersed. One of the main issues we found is where we haven't considered the minimum flow rates of the TSR properly. We've been going below the minimum turn down of the mixer and getting insufficient mixing, and metals break through at low flows effectively. So we've been modifying the TSR pumping control to take into account those minimum turn downs on the mixers. And then flocculation, taking once you've dosed the chemical, taking it and forming a nice strong flock that is filterable by your filtration processes. So for cloth filters, we're providing mechanical flocculation up front. Some of the issues we've experienced there is we found that the flocculators haven't been fully optimized. We've had them running too fast. We've had them not varying in relation to the incoming flow. And then modes of control on these dosing rigs. So we provide the same standard modes of control on all of the dosing rigs to give us that flexibility further down the line if we have to change the control. So all of the dosing rigs will have a fixed dose mode, a diurnal stop-start, flow proportional, and a feed-forward dosing control, taking an ortho-P monitor to vary the dose in relation to the incoming load. Then alkalinity as well, something important to consider. So where we're adding new chemical dosing on site, we're doing an assessment on every site to look at the consumption of alkalinity, making sure that we've got sufficient alkalinity for the nitrification process, making sure that we've still got that buffer for pH and we're not dropping the pH in the final effluent. So generally, if we believe there's an alkalinity deficit, we will phase alkalinity dosing, as in a lot of cases we found we don't actually need to install the alkalinity dosing rig because our ferric dose has been lower than we predicted in design. This schematic just gives a typical layout of a pre-dose TSR installation with the ortho-P monitoring and flow monitoring up front of the point of application, followed by the mixing, flocculation if required, then going through the TSR process with turbidity monitor on the back end, potentially to be used for a feedback trim on the pre-dosing, and then the final effluent monitoring for metals, ammonia and turbidity. So once we've got all of the right assets in place to meet these permits and we've designed in enough flexibility, we then need to make sure that we're commissioning and optimising these right. So odds are for these installations with the very tight P permits, we'd have 2 points of dosing on site, Traditionally, we'd work to 1 milligram a litre total P as the target coming off the secondary treatment process, and then relying on the pre-dose up front of the TSR to remove the rest of the load. What we found is that that's not a hard and fast rule. We want to be optimising between the different dose points on site, balancing between metals breakthrough at the back end and making sure that we're not detrimentally affecting our secondary treatment processes by overdosing at the front end. So just a bit on the dosing control. The primary dose, we generally go for a diurnal control to match the incoming load. And this works on most sites. And provided this has worked and taken it down to a fairly average total P concentration pre-TSR, we then rely on flow proportional dosing. For sites where we have that variability off the secondary treatment, potentially ones with biological phosphorus removal, doing the primary load stripping, we'll look towards that feed-forward control with that ortho-P monitor helping to adjust the dose in relation to the incoming load. Pre-TSR jar testing is something I'd strongly recommend. Once you've commissioned and optimised your primary dose point or biological phosphorus removal as much as you can, that pre-TSR jar testing will help you to understand what you need to do with your pre-TSR dose rate. It's not going to give you an exact milligrams a litre, but it's going to give you a range that you're going to start your optimisation within. And then just a bit on metals breakthrough. So pre-TSR dosing, you can potentially get your metals breakthrough if you're dosing too high or if you're dosing too low. Not dosing enough metal, you end up with your soluble metals breakthrough in addition to your ortho-P breakthrough. So it's quite hard to get somebody to turn up the dosing when the metals breakthrough is high, but it's something we've had to do on a lot of these pre-dose TSR installations. So just going through the monitoring quickly. So for all sites where we've got total P permits, we've got online ortho-P monitors, and for sites with pre-dose TSR installations, we've got iron monitors on the back end, with all of these sending alarms to telemetry to allow the operational teams to respond to issues as they're occurring. In addition to this, the operational teams are undertaking manual tests on all of these sites, and they're monitoring for a trend to see if the performance is getting any worse and taking appropriate action for these. Action limits. Historically, we work to 50% of the permit for phosphorus and iron. With these very tight permits, this is not always possible. So for phosphorus, we'll now be potentially working to 80% of the permit, and for iron, maybe working to 2 milligrams a litre. So because we're working in a much tighter operational band, we need to make sure the appropriate alarms are in place and the operational teams are reacting to these. This slide, you can touch to read later, but it's just talking about, for the very tight permits, how it's much more difficult to optimise the ferric dose to reduce chemical consumption, whereas on the laxer permits, there is more flexibility on this. So just going through a bit of an example site. So this site's got a 0.2 milligrams a litre total P permit and a 3 milligram a litre iron permit. Fairly typical biological filtration process with crude dosing, then followed by a proprietary continuous upflow filter process, again with upfront dosing. So this slide shows the initial performance when the site was commissioned. So you can see it's not quite meeting the 0.2 permit, and you can see from the graph on the left, you've got a fair variation in the amount of phosphorus coming off the tertiary solids removal process into the final effluent. So even if you exclude that higher sample on the right, you can still see that there is a fair risk of us breaching our permit. We did quite a few things on this site, including turning up the crude dosing, turning up the pre-TSR dosing, addition of alkalinity dosing, optimising TSR backwash. And with a combination of all these factors, we've managed to pull down the levels of total phosphorus in the final effluent to a much more manageable and comfortable level against the 0.2 milligram a litre permit. Though conversely on this one, you can see that we've gone from sitting at 0.5 milligrams a litre iron on average in the final effluent up to 1 milligram a litre on average, with values going up to 1.5, 1.7. So that's just showing that it's going to be a bit of a balancing act. You're not going to necessarily be able to achieve your very low phosphorus and the very low metals at the same time. To summarise, there's no easy solution. It's always going to be a combination of factors. It starts off with getting the design right, providing the right assets along with the right flexibility, so things can be altered later down the line. Then it's spending a good amount of time commissioning and optimising, getting those assets to the best place they can be, and then going on to the operational teams. We need to get their buy-in as early as possible, making sure they understand the processes, understand how to troubleshoot them, and are on board with the maintenance regimes, making sure that is in place. All of this needs to be done together to make sure we can meet our low total P permits and the associated metals permits. Any questions?
Thank you. And straight up there.
Hi, that's really interesting, thank you. My question is around, on your later slides you show some phosphorus data. Have you run those same data points through the sill to see how well it performs and whether you really do have a problem, or do you not have the sill permit also applicable on these sites? So even that, what would be seen as an exceedance on a single data point, you could actually be completely compliant.
So what I was trying to show there is that we were getting a fair amount of variation in the performance, though you could say, when you look at that data, the average, excluding the outliers, you're compliant. Looking at the online monitor data, you can see that we have got a fair amount of variation. We weren't fully optimised. In some ways, we were actually fortunate with the sample data, but yes, we did take that into account, and on the later data you can see that we were compliant the majority of the time with that permit on average, not taking into account, well, there were a lot less outliers, let's say. Yeah.
Hi, Jeremy Black from United Utilities. Tom, thanks very much. Fascinating presentation. I've got lots of questions, but I'm just going to ask one for now. When we've looked at jar testing and choice of chemical, we've often found that ferric chloride outperforms ferric sulfate in terms of molar ratios, but it's left us with a bit of a dilemma because we actually prefer ferric sulfate for supply issues and safety reasons. And I was wondering if you'd had any similar experience from your choice of chemicals at Severn Trent.
Previously, if we were dosing into activated sludge process, we would have gone for ferrous chloride and relied on the oxidation within the process. We've struggled to get ferrous chloride recently, so we've been going more towards the ferric sulfate route. The ferric sulfate tends to be a good performing coagulant, and you also don't have the chloride issues, with the chloride being the bit in the coagulant that leads to the problems with stainless steel elements within the dosing system. So we do try to design it to accommodate for the different coagulants, but the ferric sulfate does tend to perform better. But we, as I say, historically we've generally used ferrous chloride, ferric sulfate, or PAX or aluminium sulfate. We've not used the ferric chloride so much, but again, availability at the moment dictates ferric sulfate tends to be the preferred.
Probably got time for a couple more questions if anyone wants to ask any. Keen for tea. Can I ask one quick one, which is, obviously we talked about supply issues at the moment and with chemicals and the tightening metal permits. Has that changed your strategy in any way? Are you looking more towards biological P removal as the upfront stage?
Yeah, so I suppose I didn't touch on that so much. So for the primary phosphorus removal, so we will look at biological phosphorus removal in addition to the chemical removal options. If we can do the biological phosphorus removal, we'll definitely go down that route. But to meet the sort of very tight permits, you're always going to end up with at least one dose point on site, whether that's a top-up into your activated sludge system or in up front of your TSR removal process. So, yeah, I think to meet these very low permits, it's going to be a combination of biological with potential with the chemical dosing. And where you can't do that biological element, you're going to have to rely fully on the chemical dose solutions, which, yes, do hold quite a risk if we're running out of chemical. But it's unavoidable in some cases.
Okay. No further questions, so I'll let you all get to the afternoon break and the tea and cakes. Good afternoon again. Welcome back. We'll make a start again. Just on the programme, we've got three presentations on the programme. Unfortunately, the final one from Helen at Thames Water, she's unable to make it this afternoon, so we'll just have two more presentations in here, so you can dive next door if you want the third presentation of the afternoon into room 1. Again, we've got, I'll remind you, we've got the drinks reception between 5 and 6 in the exhibition hall, and also please do try and find 5 minutes to look at the posters and vote on those, please, on the way into the main exhibition area. Okay, so the first presentation this afternoon is from this session is Andrew Baird from WPL. Again, if you want to put any questions on the chat on Hopin or the Q&A session on Hopin, feel free to do that, and we'll take questions after as normal. Over to you, Andrew.
Right, afternoon everybody. My name is Andrew Baird. I'm from a company called WCS now. We changed in January, we were acquired. WCS are owned by the Marlowe Group, which is effectively a compliance group. So we're a much bigger organisation now, and rather than just spending 1% of our turnover on R&D, we're now allowed to spend 0.5% of our turnover on R&D. So there you go, the joys of joining a big organisation. Hopefully, this is the right one. What I'm going to cover today is not specifically a high-tech technology, it's more a view of where we are with pea removal. I spent an hour this morning with DEFRA, Natural England, looking at pea removal at a domestic level, obviously because they all contribute as well. What I also want to do is have a look at some of the technology that's already out there. I know that a lot of the guys here today have got some fantastic technologies, getting down to very low levels of P that are being demanded at the moment by our governing bodies, the Environment Agency. But you also have a lot of the utilities, a lot of the commercial domestic already have equipment on site that's capable of meeting some pretty tight consent standards in terms of P. So what I have a look at doing is, you know, can these assets that you already have be leveraged, made to perform better? One of the things is that we're having, as a business, we cover numerous sort of siloed areas, basically domestic, commercial, which is your holiday parks, and they're fairly large contributors of P into the environment. You then look at industrial, okay, it goes through a lot of it goes through the sewer into the water utilities, but we also do quite a lot of kit for sites, the rural sites, dairies, this type of thing, where they're discharging through their own on-site treatment works that work to a greater or lesser degree. And then obviously we supply into the utilities, we do higher kit into the utilities, we do below ground sewage treatment plants, probably more known for smaller type applications up to about 5,000 population, rather than the guys that have been talking today are talking about much bigger applications than we do. But there's still quite a high contribution of P into the environment from these applications. Obviously we're governed by the Environment Agency on your consent to discharge. What's come in now is planning requirements from Natural England. I don't know if people are aware of this, a couple of people have mentioned it today, that if you put a planning application in for a new development, Natural England are looking at nutrient neutrality. This means that you cannot contribute any further P or nutrients into the environment. So if you're a single dwelling and you've got your little house that you want to build and you go for a planning application, you'll be asked to get nutrient neutrality. And of course, obviously through the water utilities, you've got Mogden formula for industrial applications. I'm not really going to cover industrial applications, but certainly going to do a little bit on the domestic side of things because the contribution from there is quite large. I think everybody's aware of the utility applications. These aren't my figures, by the way. I just pinched these off the internet, so if they're wrong, blame somebody else. So you got AMP7, and you got the Yorkshire Water one there that's got 80 new permits. Wastewater, 63 schemes, as far as I'm aware, down to 0.3 milligrams per litre consent, and 25 sites down to 1. 25 sites down to 1 are fairly easy. We do a very simple basic microscreen, 20 micron. If you do front-end dosing, you'll certainly hit a 1 milligram per litre, and I'll show you some data on some work that we've been doing on that. On the domestic, what I was saying was, in England, in Scotland and Wales, they actually have a registration of how many treatment plants are going in. In England, they stopped doing this a number of years back and brought in general binding rules. Under a population of 50 people, you don't need a consent to discharge. You go under general binding rules, and if you have a piece of kit that qualifies under EN 12566/3, you can throw it in the ground and off you go, no problems at all. So no consents. There is over 30,000 in England units that are installed, doing round about 750 litres per unit per day, giving you total treated effluent of around about 8 million litres a year, contributing about 130 tonne of P into the environment just in England. That is the England figure. Because we don't actually register or have any kind of view on how many of these treatment plants are going in Scotland under SEPA, they have nearly 10 times the amount of treatment plants we've got. So either we've got better mains connection or nobody really knows what we're putting into the environment. So if your baseline is being skewed by the fact that you don't know what's going into the environment, how can you set such tight standards for the utilities? Is one question. One of the reasons I've got this up here as well, this is a product, I hate to say it, this is a product we're developing and you can buy one very soon. But basically, a small package treatment plant, for those people that don't know, is something like at the top there. And we've been running trials by just introducing daylight lights into effectively what is an AS plant. Typically speaking, on an AS plant, we'd see about 50% removal of nutrient across the board. When we introduced the daylight lamps into the Diamond sewage treatment plant, that's the one, we started to see a 90 to 95% removal rate on P. We were only monitoring on P, and then we thought, well, this is looking pretty clean, a lot better than we would normally see when we test our plants. We normally go with a glass of, stick it in, scoop some out, have a look at it and go, that looks pretty clean. So we went a bit further on that. We're now finding that BODs are coming down to about 4 milligrams per litre when typically you'd see a 20, and suspended solids are coming out at about 6 consistently. How do we know? And this was obviously with the options. Let's jump back a step. The options for actually getting P removal and getting compliance for your planning permission, a lot of people are suggesting chemical dosing. So if you imagine chemical dosing at a domestic level, that you've just got home and your chemicals run out and you've got to trudge down the garden in the middle of winter with your 5 litres of ferric chloride, stick it on your dosing pump, set up your dosing stuff, and away you go. It's not really probably the best way of treating for P at a domestic level. So after putting daylight lights inside an AS plant, we looked at flow across the lamps because they fouled and they started to get dirty, so we increased or improved the cross-flow efficiency across the lamp, which reduced the amount of algal growth that we saw there. Again, how do we know it was algae? We're not 100% sure at the moment because it's still pretty early days, but we're pretty convinced it is. We've done chlorophyll testing on there. Without daylight lights in there, we're around about 5 milligrams per litre of chlorophyll. With daylight lamps, we're up to about 50 to 70 milligrams per litre of chlorophyll. So we know there's something growing in there, and obviously the results prove it as well. Where you see the 11th of the 3rd, I think it is, where we've see the two lines of the incoming and the outgoing on P. That's where it failed and it broke down. So, and at the beginning, we didn't have the daylight lights. So at the beginning of the graph, you can see we've got very little P removal, and where we've had a failure, we've had very little P removal. But we're now seeing significant amounts of P removal. How does this benefit a homeowner? What Natural England are introducing is offsetting. So if you can't remove the P, they're now going to offset. And you can buy credits. These credits in the Solent area, typically speaking on new development, are anything between, for a single property that you're developing, varies between £4,000 and £15,000 extra on your build cost for a single development. So 10 houses, 150 grand. So yeah, buying credits and offsetting something that you don't know the level that's going into the environment to start with is a bit difficult. So I say today is more about trying to get people behind the fact that you should be talking to each other a lot more, and we can see where we get to. Commercial, again, another product you'll be able to buy very soon. Some zeolite beads. FDA have sponsored the development of this in the US. We came across it. We've done some trial work with Portsmouth University that was reasonably successful. And one of the issues that we had was how we're going to carry and deliver this stuff at a commercial level. So for a holiday camp, you don't want to be wheeling barrel loads of this stuff around and digging it out. So we've taken a traditional sand filter that we produce, very simple, basic system. And we filled it with zeolite beads, took it to Portsmouth University at the Petersfield test site, which is a Southern Water works. And they did some trials for us. And the results, on the face of it, look extremely promising. We still got some further work to do, some jar testing. As you can see on the right-hand graph there, the blue being effectively P in, and the right-hand, or the green, being effectively P out, total P out. So we are getting decent performance out of these particular beads. One of the areas that let us down a little bit was removing total soluble P. It seemed to struggle a little bit on that, so we're going back to the lab. We're going to look at retention times and see if we can still retain it in a basic sand filter that basically works on a pump and by gravity. So the commercial side of things, we think we're getting sorted out. The domestic side of things, we think we've got a reasonably good solution for that. So that brings us to the utilities. If we do our bit down at the bottom end and remove all this phosphate from the environment, remove all these nutrients from the environment, does that then impact on what the utilities have to achieve? And could they actually then look at leveraging their present equipment to meet the requirements of catchment rather than these blanket 0.1s, 0.2s, 0.03s type consents? As I've demonstrated, I haven't put figures in for the commercial volumes going there, but if you imagine certain catchments in Devon, for example, where you've probably got 20 or 30 very large caravan sites, holiday parks, this type of thing, and maybe one or two small villages with the works on, but they're imposing a very tight consent on the works, and virtually nothing onto the holiday parks. I think a little bit more collaboration at a catchment level, so from a utility perspective, maybe talk to the catchment and see what can be done to actually reduce nutrient contribution into the environment. As I say, rather than this, I mean, unfortunately for the utilities, you're a massive target. You are pumping loads of stuff into the rivers every day, day in, day out. So you would expect to be the first target. And I tend to agree. The really massive works, yes, they have to be controlled. But your smaller, more rural works, is it not more about catchment and contribution from everybody within that catchment to get nutrient contribution down? Within within our company, we basically do HiPath, which is a fixed film process. People here may have come across it. We do sand filters, basic sand filters, but we've seen on basic sand filters with zeolite getting down below 4.5. The zeolite, we're estimating, is going to last about a year. So in terms of maintenance, we've designed it so you go along with a vacuum tanker. You suck out the zeolite beads and you throw a load bags more of zeolite back into it, so maintenance is reduced. We looked at DAF, yes, but again, you're into big chemical dosing. We've recently trialled one of our micro screens, which is a basic screen. It's not a depth filter or anything like this. It's pretty much 20 micron, and we're getting down comfortably to 0.5. That was at a peak, we were hitting 0.5, but generally speaking, after optimization, they were maintaining about 0.3s, 0.4s without any problem. They were chemical dosing on site, and initially they were pre and post chemical dosing. So we said, well, why don't you stop doing that? And they went, okay. So they just went for front-end chemical dosing, which is obviously, again, your control levels, your infrastructure, costs, etc. go down. And then post-optimization on the back end, yes, we were only going in at 1, but we were maintaining, from this data that we were provided with, I believe we continued to maintain around about a 0.4. And again, it's, that's just optimizing your site. We didn't need fancy equipment in. And you have to remember, I'm only talking about sites up to maybe maximum 5 or 10,000 population. I'm not looking at the big sites. Our kit is just not suitable for that. And I think Vicky, the previous speaker, turned around and said it's horses for courses, the right piece of kit to meet the right requirement. But before you invest in capital, have a look at your catchment and persuade the environment agencies they should be doing the same thing. Chemical dosing, I don't disagree with chemical dosing, but not at the levels that we're talking about. It's very difficult to control, it's difficult to monitor. An unmanned works, you can overdose. If you overdose with ferric, basically you're adding iron back into the water, which is great for algal growth, which causes eutrophication. If you start adding aluminium into water, potentially if you overdose or you have a spill or an issue, you then got fish kill and these types of things happening. So, yeah, chemical dosing is a requirement and is a requirement in a lot of sites, but some sites possibly not. Benefits of looking at alternatives, say with the domestic one, if we can get algae to grow in an AS plant by just sticking in 140 quid's worth of daylight lamps, great. I can say that now because we've just actually filed a patent on it yesterday, so I was going to show some pictures of it, but I didn't have time to put it in because we only just filed yesterday. So yes, daylight lights in there, you seem to get much better removal rates on all parameters. So this is really the point of, I guess, of sort of the presentation was about. Yes, it's to show that we are looking at technologies. Yes, we're a company that is developing things and we're trying to move stuff along. But I strongly believe you need to look at catchment in its entirety. Regulatory standardization is one of my biggest banes at this moment in time. To give you an example, the Environment Agency, when they calculate on population for water consumption, it's 150 litres per person per day for when we're sizing a plant. Natural England have come up with 110 litres per person per day. So that means that the level of concentrations you see in milligrams per litre vary. So you've got EA got one set of rules, Natural England got another set of rules. So there has to be standardisation. We had a meeting this morning, which was hosted by British Water, and the EA and Natural England both agreed that they just don't talk to each other. So you know, maybe a bit more communication if they're not talking to each other and we're not talking to each other. Utilities, utility suppliers for the big sites. You can drive your technologies down. We can look at packaging them, making them more simple for the unmanned site. Data sharing, great. Utilities are absolutely fantastic at sharing data when you have a problem. When you don't have a problem, can we get any information from you? Probably not, no. No, it's only when it's going wrong and they're on their phone going, can you come and fix it, please? Well, what's wrong with it? Well, it's not doing what it's supposed to do. Well, fine, but do you supply data at the end of the day and continue to supply data? No, you don't. And again, identifying the best combinations of technology. It's a really simple thing to do. So my message pretty much really is, yeah, other than come and buy a bits of kit that I've shown today, and that would be fantastic because that keeps me in a job and paid. But communicate a bit more. If everybody in industry, across the board, from domestic manufacturers like we manufacture domestic, through to massive guys who supply huge bits of technical pieces of kit, communicate a bit more, and I think we'd all find a much better solution. And that's pretty much it. And no questions.
Thank you, Andrew. I'm sure there are some questions.
It's pint of lager.
Thank you. Peter Pearce here again, Farmer Fisher. A comment first of all, or comment and a question. If you're talking to DEFRA and the Environment Agency, are they listening? Because it seems to me that, you know, we're all agreed, I think, in this room that these ridiculously low phosphorus consents on tiny works will have unmeasurable impact probably in terms of the environment. So I'll be interested to know if they are actually open to listening finally. But the question is intriguing what you're saying about your daylight lamps on your activated sludge plant. Presumably that's on one of your small activated sludge plants, yeah, like the Diamond one or something, where there'll be a fairly rapid surface renewal. So the activated sludge will see the daylight quite frequently, if you like, and I would suggest a lot more frequently non a 5 metre deep, you know, large activated sludge plant. Your thoughts on that, really?
Yeah, I haven't got a really massive activated sludge plant in the yard. It'd be nice, but we haven't. In answer to your question, what we found was that the recirculation rates within the AS plant were quite critical. So we maintain a certain level of recirculation or circulation over the lamp through effectively an airlift. So we put the lamps actually within an airlift tube, and we can control the amount of velocity. If you don't have enough velocity, you get fouling of the lamps and you don't get any transmission. If you have too much, we haven't actually tried it with too much, to be honest with you. Well, maybe you give that a try. But that's to do with energy. The less power consumption you put in, the better, because your carbon footprint goes down. We haven't tried it on the large. The idea of the process is a bit that we've looked at patenting, or that we're looking to protect the IP on. But we're more than open to share stuff with people. If they want to try it on a large AS plant, we'll quite happily come along and talk to them and see if we can make it work on a big plant. As I say, we're pretty close to thinking. We've been running the AS plant now for about a year and a half. So we're pretty close to thinking that it does actually do something and it's not just wishful thinking on our part. What was your other question? So, do DEFRA and EA and everybody else listen to us? Well, they don't listen to each other, so I think we've got no hope in hell, to be honest with you. There's one more. Got two questions.
Earlier you said you weren't quite sure what was growing on your lamps. You said it might be algae. Do you think it will impact if you had secondary settlement tanks? Will you result in floating sludges and such?
The Diamond Products, it's an AS plant, but it actually, because it's a packaged plant and we actually just take raw sewage, it's not screened, we don't take anything out. It goes into a central aeration chamber where you get the AS process. The reason why it's a diamond shape, effectively, there's an outer section which acts as a settlement tank. That then, the solids drop down to the bottom again and are actually picked up by the airlift and brought back into the process. So we get very high sludge concentrations within the aeration chamber. Whether it's algae growing or not, we don't know. We do know there's a high content of chlorophyll. And at the moment, we intend for the next 12 months is to quantify that, and we're partially funding some work with Portsmouth University, and we're going to have 2 students working on that in the next month or so. Right, can I go now?
Just a quick question. What's the final fate of the P? Are the solids coming out in the normal route with the phosphorus in it? How are you getting the phosphorus out of your reactors?
Good question. When we measured on the out, well, you saw the in and the out, we also had a look at, are we just shedding, if it is algae or whatever it is that's growing in there, the chlorophyll-based material, are we just shedding a load of that rather than solids? The answer is no, because we did chlorophyll on the outfall as well, so that we know that we're retaining it within the sludge. Now the issue with this is because you're doing spot samples, the minute you turn the back, the little buggers may run down the drain and all discharge themselves into the environment. So until we start running proper sampling regimes, it's not 100%, but we believe strongly that we're retaining the P within whatever's growing in there, and that again gets removed periodically with the sludge from the AS plant, we think.
Okay, Andrew, we'll let you go. Thank you very much. The next presentation is Rowan Luck from Severn Trent Water.
Hi everybody, good afternoon. Hopefully you'll stay nicely awake for my presentation. It's the last one for this session, so I can go on for quite a while, can't I? At least 40 minutes. Oh, brilliant, I'll do that. That's great. So talking about our experiences at Severn Trent on AMP6, call it the highs and the lows. All of my stories do have a happy ending, so you'll be pleased to hear, with a few adventures along the way. Right. So, I'm going to share a few experiences with you around AMP6, particularly looking at the capital scheme process commissioning. At the start of AMP6, I was running a team of process scientists, process advisors and wastewater, and then moved on to now working with a team of process engineers who also do commissioning activity on wastewater sites. So wastewater is my thing, love it. It's my favourite topic, other than biological pea removal, which is my most favourite topic, but that's for another conference perhaps. So let's talk through our 3 wastewater sites. Then we've got a site called Booton, Dinnington and Harby, all in the East Midlands. Look at the outline capital solutions we're going to apply and the challenges that we saw to deliver those schemes, and share some of the wider learnings from delivering the AMP6 total programme for Severn Trent sites. So have to share this map every time. I think it's contractual. So it's our Severn Trent map, and we also have our 7D, or Hafren HD we call it, because it's too hard for us to say, but we have got some very good Welsh speakers in our team now, so I will be practicing that one. So right in the middle there is Birmingham. Oh, that's the wrong one. We've got a big catchment. We've got 1,000 sewage works within our catchment there, and around 94,000 kilometres of sewerage mains as well. So it's a lot of sewage works, a lot of rivers, and a lot of population as well in that section. So a lot of people have covered reasons why. The the dots on here, if I can get my thing to work. There we go. We've got agriculture and the water industry being the largest impactors on phosphorus and nutrients within the watercourses. On the map on the right here, you can see where the nice blue areas are, the water quality is much better. Where you're seeing going towards the ambers and the reds, the water quality is much worse. So all part of the Water Framework Directive, trying to move towards good ecological status on all our watercourses across the UK, which is it's a big challenge, and it takes a lot of impact, a lot of effort from a lot of different parties to achieve that. But today we're just going to focus on particularly chemical phosphorus removal. So quick chemistry lesson, but hopefully you all know well your chemistry from the other conversations you've had today. Dosing metal with a metal salt with orthophosphate combines to give you a metal precipitate, which is removed from your sludge route. I've got a diagram there of, get these things the right way around. A nice little picture there of a really basic dosing installation into an inlet works on the right there. You can dose it many different points in your treatment process, into primary, secondary, or into final and beyond. Tom O'Shea from our team also talked well about metals permits and also additional alkalinity, which you'd need to try and achieve the best outcome for your site and for your permit. So on to our sites. Our first site is a site called Booton. It's a medium-sized site. There are a few more stats later on for population equivalent and flow rates for those that like the data. It's near Mansfield in Nottinghamshire. It is a biological filter works. Prior to our capital scheme, it had both plastic and slag media filters running in parallel. And we were dosing ferric sulfate for existing permits for urban waste. So we're looking to see an increase in population equivalent over time, and looking to achieve a tighter ammonia and tighter phosphorus and tighter BOD permits, all part of the capital scheme for this site in AMP6. Now, Andrew talked from WPL, now you've changed your company name. You can see on the side there, this site has historically had plenty of problems. Many thanks to our colleagues at WPL for helping us out to keep these sites running until our capital schemes are delivered. So big thanks to all our companies that help us with maintaining our temporary treatment to keep this site going. So overall, lots of problems with this site in the run-up to the capital scheme. Lots of things to design and to get right with this capital piece of work. So basic scope, reinstate the mineral beds, new ferric dosing rig, 3 points of dosing, new caustic rig, new ammonia removal plant, new tertiary solids. Doing all this while maintaining the actual current site compliance. So there's a lot of work happening on this site. So what does the site need to meet? It needs to hit a tighter BOD. The ammonia is going down from 5 to 1.2. And it's also got a 0.2 phosphorus on this site. Now, I've put the site diagram on here. We've had quite a few of these today, but it's a very simple, very common process flow diagram for many medium-sized sites. I'm sure you've seen this before. What you don't see is all the additional temporary kit to keep this site running well prior to delivery of a capital scheme. Multiple SAF units, that's submerged aerated filters. Adding bicarb seasonally to maintain our phosphorus and our chemicals working well. Sloughing issues. Tons of extra site visits and operational activity and extra tankering to keep this site well and compliant. So let's move on to, hopefully people can see that. It's not too blurry, that one. It's a bit of an off picture. So the main changes we've done, we put in here, was we've put in the trickling filters are now all refurbished to have a slag media. I've got a dosing point in front of the humus tanks as a dosing option. Dosing option to the primary tanks. And the additional units are, again, the MBBR, the Veolia style ammonia removal plants. At the back end,
more dosing again, so we're talking dosing a lot today, prior to a pile cloth filter with upfront chemical dosing on there. So lots and lots of work to do, lots of different things to try and achieve with one capital scheme. So quick picky of the ferric dosing. So we've got the 3 separate dosing points and a common spare. And on the right-hand side here, that's just a photo of the caustic rig, sodium hydroxide rig. Alongside that, as Tom mentioned earlier on, we've got pH probes as well installed to make sure we don't overdose, underdose, to protect the site. Okay, so let's get to the nitty-gritty of the process commissioning. The pictures I've put in on the right there are the works completed, looking nice. You can't see a bit of overland pipe work there at all. So during commissioning, these are some of the things we found, the problems and issues we had to deal with. So the top one there, looking at trying to run with additional alkalinity dosing from temporary systems. Never easy to run from IBCs or equivalent when you're trying to progress your program, progress your project without compromising your final effluent. You sometimes have to use temporary systems for your alkalinity dosing. So it's really not easy to keep those systems up and running. A few hydraulic teething troubles on our TSR. Bit of flooding, bit of overloading, bit of bypassing. So it's always have a few issues, sorting a few things out there, getting flows just right, getting systems just right. So again, good collaboration between our suppliers, our engineers working on site, and our process commissioning staff and our operational teams to sort those things out. Now, and also, you might remember before we had 3 dosing points, crude, humus, or pre-TSR. As we're going through the programme, we found that we were having a few issues dosing into the humus tanks, and as soon as we could, we moved across to the crude dosing only with the caustic in use, which really brought us back round into more control. The MBBR was set up for the ammonia removal fairly early on in the programme, which allowed us to refurbish our trickling filters without risking our ammonia compliance in that situation. So a bit of good planning there to make sure we can do our enabling works and resolve the site. And also, a nice little positive at the end there. When we put on the dosing prior to the cloth filters, we found that it did give us less problems on iron than we predicted, so a little benefit, a little positive there. Now, looking at this graph at the top there, I've seen quite a few of these, and I like that today. We're all showing some really nice stories around starting commissioning. The last piece of the puzzle was to turn the TSR dosing, which sits in here, dropping us down nice and low. So the purple on there is the ortho P, which is on this axis this side, sitting around 0.1 there. And iron on this axis, the blue line, trundling along about 0.4 across the way, which is excellent on a 3.5 iron permit. So, a few bit of stats on there, looking at total P towards the end of our commissioning activity, hitting around 0.11. So 0.2 is the permit, hitting 0.11 on there. And on the photograph there is one of our commissioning team at the time, Mo, just showing off nicely for us the final effluent monitors. Second site, Dinnington. Not quite as exciting maybe in some ways, not so much to build and remake. Medium-sized works, slight growth, going from 1 to a 0.2p. So we didn't have masses to do there, beyond changing, we talked about a bit earlier on about the ferrous chloride, ferric sulfate and other chemical options. For this site, we went with introducing ferrous chloride into the ASP as opposed to having it with ferric previously. So that's a big step change for the site. And putting in ferric sulfate at the back end with a new tertiary solids removal plant. So, and decommissioning our existing samples that we had on site from the previous AMP. Quick site diagram. So, Need to meet a BOD of 13, solids 30, ammonia 2.5, and again, our lowest 0.2 total phosphorus. The capital solution there, simultaneous dosing into the settled sewage, into the ASP, and dosing into the TSR. So you can see on the diagram there, no, not massive changes, just changing the chemical here to ferrous, adding in a chemical ferric sulfate here, and putting in new tertiary solids removal. So, a few issues and stages we went through the actual commissioning. Quite tricky, complete changeover of a chemical for your bulk of your chemical, bulk of your P removal, changing from ferric to ferrous. Typically, we like to go nice and slow with our commissioning activity and turn things up slowly. Not this case. Switch it on fast and speed it up fast. Now, many of the issues on this site were not really commissioning issues in terms of we weren't doing the right thing. But the first one here, a slight error on ordering for chemicals. We ran out of product for a number of days. Once back in, quickly came back up to good compliance. A bit of a problem on a pressure transducer that completely failed, which did cause quite a major incident and major spillage on site. So again, another delay to the scheme on there. Now, we also had a countrywide and company-wide incident about reduced ferrous chloride and ferric sulfate supplies across the period of time of commissioning here, which again delayed our scheme in terms of optimisation work. But another key thing we did during commissioning was to make sure we did some on-site jar testing to correctly assess the amount of dose we needed to add at the back end of the work to protect any breakthrough of iron dosing on there. So pleased to say, yeah, it's a success. It's met its 0.2 permit. The dosing's working well, but we're still always looking ahead, keeping an eye on the residual risks. We need both things working well together, and we need to look, as ever, continuing optimisation to make sure we're making the best use of the products and chemicals that we use on our sites for the environment and, of course, for economics. Now, I like these graphs because there's loads of stuff on these graphs. Not my graphs, thanks to one of my colleagues on here. The big block of blue is the ASP dosing rate, so hopefully you can see on there that's going up over time. The purple block is the TSR dose being put on, and we're just looking at the iron data, trundling on the bottom here. Lab monitors, the iron monitor and on-site testing, hitting a bit of a wobble towards the end, but still below 1.5, and then settling down to be well in control on a 3.5 permit. My third site, you'll be pleased to hear, we're moving towards the third one now. It's a site called Harby. We're in Leicestershire now, at least we're moving around a little bit. So, a site near Melton Mowbray. Now, the key thing about this one, and I'm really trying to avoid bad jokes about cheese, but this site has a future population equivalent to design to 33,000. Of that number, the trade is almost 30,000. So it's a massive trade impacted site. Needs to meet a 0.25 total phosphorus permit, along with a 2.5 milligram per litre iron. So tight iron, tight P, but this site doesn't have an ammonia permit. So does it make sense? It does when you look at the overall. So within the Water Framework Directive, it's a catchment approach. And this just shows you a little bit about how that's been applied to one of our catchments. So all these are different sites that drop into the same watercourse, which is kind of effectively trundling along here. To achieve our good ecological status, we need to apply varying permits, conditions on phosphorus to achieve that across the way. Harby is a big site. It sees a lot of phosphorus load. Even though there's no ammonia permit, to help and to make sure the river quality is good, it hits the 0.25 permit as required in the water framework and the WINEP determinations. Now, it's not an easy site to deal with. it's got a large input from a cheese manufacturer, really strong crude sewage, really strong coming in there, and a massive impact on biological loading. So as a consequence, the Harby AMP6Q scheme has had a very complex history with many debates and many ongoing meetings and decisions around what is the answer for Harby to achieve these permits. It took a long time to reach that AMP6 design that we have applied. So what have we put in? So our capital solution, we went through many options around activated sludge and came back round to, okay, we're going to apply this system. We're going to dose at 3 points, and we're going to add on a tertiary solids removal system at the back end. For this site, we used the filter clear system. So, don't know what I've got. Ignore the fact that it says ammonia on there. That's a complete lie. It's not got an ammonia permit, so apologise for that. So, commissioning this kind of site was a bit dreaded. It went through a couple of different team members for who's going to commission this site. It's quite a challenging one. I went to one of our team, Adam, who took it on in a good spirit. So, one of the big issues we were talking about is trade waste and iron dosing. Cheese waste and iron dosing doesn't sound like a nice combination, does it? So, getting over these issues, we again employed the infamous jar testing to assess what is the right level, and also a really good tool for persuading operational colleagues and others that yes, we do need to increase the dose rate. We will see a benefit. It's such a straightforward activity, but it really can help people see real reason as to why you want to increase dose rates when it may seem counterintuitive. And the other biggie, we had to really make sure we're on top of the sludge movements for the site. So a couple of key points there for any of the schemes that you come across for getting low P. Keep an eye on the sludge. Just to help us out, we had extreme weather events and flooding at the site across the time of trying to commission. Dealing with some existing site limitations as well around the not so good flow control to site, which had to be dealt with and resolved additional to the scheme. We talked about cheese waste. There's real variability in the P loadings to this site. I'm sure you can imagine cheese manufacturers, and you're making your Stiltons and so on. It's quite variable across the year, especially you run up to Christmas. A number of final effluent monitor faults that had to be dealt with and resolved, which was dealt with and resolved, and working carefully around the iron levels in the final effluent, getting the dose just right, getting the setup just right on the filter clear unit to do that. But a couple of slides ago talked about it was a tricky scheme to get a resolution for, to come up with an actual answer. What are we going to do? Within that, over time, it can really be difficult to build back up the operational confidence in the solution you've applied, because it's been talked about for such a long time as a site that's very difficult to do. So it's taken a lot of time to build the operator confidence in the solution, demonstrate it, and support the operational team so they are confident and they work the site really well. So, successes. We met the 0.25 total phosphorus permit using 2 of the 3 dose points that we could use. We could still use all 3 if we wanted to. The site does remove ammonia anyway, and we've maintained that level of ammonia removal, and the alkalinity levels were absolutely fine. With the introduction of the ferric sulfate dosing. The TSR was optimised and the performance improved, and the residual iron levels much improved and more stable. So thinking about recommendations for this site as well, because we may have delivered the site, but we still need to keep on top of it. So ongoing monitoring and optimisation, and looking across the seasons with the variability. And regular refresher training for operational teams to keep them really on top of this site. So quick graph there. Got iron measurements on this side, improving all the time, across time. Permits 2.5, the purple line. Phosphorus results, again improving across time. 0.2 is the permit. So we've seen lots of these nice graphs today, which is great, showing good improvement across time with commissioning. That's my 3 sites. So that's the highs and lows, just a couple of notes there. All of these site schemes were considered a process high risk due to the nature of the low phosphorus and the fact we hadn't done this before. So all new territory. Each scheme took a bit of time. A thank you to my colleagues and the team members, and some people have moved on to other roles now, but thanks to those guys for helping and deliver those schemes so well. And the sites have maintained their averages. I've just quoted their compliance averages of 0.1, 0.1, 0.13 against their permits, and I've put in the latest data for the latest results. So they are doing very well. We'll think about if we want to optimise those a tiny bit, but they're doing great. So that's all the numbers. Across AMP6, the bigger picture, we delivered 104 new permits in place by the end of March 2020. 39 of those were 0.5 or below. And of those 12 of them were really low. A couple of the key things we've learnt around this is assumptions get made about the efficiency of existing assets. Double check, recheck and challenge. Think about other capital schemes happening at the same time and maintaining your permits. Always be ready for delays. That picture there is a picture of a point of application dosing point. This little water in here, it's not water, it's all ferric leakage. So you will have problems and delays as you go through. Don't lose heart on that. Site preparation is major. Sludge management, temporary treatment and shutdowns. Careful consideration to keep compliance. And then a few more things. Not having your lab facilities when you need them. A nice sunny windowsill can help you do your jar tests fairly well. And everything else, construction delays, existing permits. Let's chuck Brexit in there. All this happened over AMP6. Brexit, short-term shortages, global pandemics, staff turnovers, restructuring, and now we've got driver shortages. So the challenges keep on rolling. And then there was the weather. I think we had several major storms across the time and major flooding events. And that's just my leaves in the can example for anyone who has found a few problems there. Definitely more phosphate in there than you need. Who made it all possible? Across AMP6, it was a big programme for Severn Trent. Just a picture of the commissioning team having a 5-minute break during a volunteering day. But there are a lot of people involved in delivering these schemes. Collaboration, of course, is key. It's been mentioned a lot of times. You can't deliver these schemes without support and help from others. Nearly done. And finally, Severn Trent delivered on its obligations to get to low levels of phosphorus. And a small number of our schemes from AMP6 we're still involved with directly for optimisation activity and further improvement. So it was a big programme, so I'm not surprised. That's pretty standard, I think, across an AMP into the next AMP. And we're now working on the delivery of AMP7, whilst trying our very best to apply what we've learnt from AMP6 to ensure better delivery of AMP7 and beyond. And that's it. I may have gone a bit longer than I should have, but I apologise.
Thank you, Rowan. Well, we haven't got another presentation after this, so we do have time for questions if anyone would like to ask any questions. Just coming behind.
Wendy Rostron from MMB. Dinnington, you said you decommissioned some old sand filters. I'm just wondering what they were, and did you consider using those as your tertiary treatment?
Yeah, they were at the canister type, just downflow filters, so we reused them elsewhere on other sites that weren't pea removal sites. We didn't, for this application, at that point, we didn't consider them for reuse for this point. They also didn't treat the full flow. Particularly in the last AMP, we were designing to treat a proportion of the flow where we have iron dosing as opposed to the full. So they didn't fit the brief, and we went with a replacement and reuse elsewhere for those.
Okay, great, thanks. Thank you.
Anybody else? Questions? Pete just keeps moving around the room, so we think it's somebody else.
Yeah, Peter Pearce here again. Sorry, I've got to keep your questions going, keep you on your toes. But
Yeah,
thank you for a very lively presentation at the end of the day. That's a very good job, so thank you for that. The question was on the, is it Harvey, the site with
the cheese waste,
the cheese factory? Yeah. So the domestic's only about less than 10% of the load.
Mm.
What's the nutrient balance on the cheese effluent, on the cheese waste? I mean, traditionally they're deficient in NMP or low in NMP, let's say.
The cheese waste, particularly high in P, in phosphate, would we're getting some values up to 60s and 80s for the combined sewerage coming into the site. I don't know about the nitrogen, to be honest, Pete, for nitrogen levels in that, but
I'm getting my different trade waste mixed up then. So actually, okay, so your cheese waste is higher than domestic.
Yeah, lots of phosphate in there,
Right.
lots of alkalinity in there, calcium yummy, you know, that's what you got there.
That's good. Thank you.
Thanks.
Hi, Jeremy Black from United Utilities. I noticed on the scope you have iron monitors, online iron monitors for your final effluent. Have you considered doing away with them and just relying on turbidity monitors, or would that be too high risk?
I think it would be too high risk for dosing back end, for chemical dosing at the back end of the site. The turbidity monitors are relatively reliable, but all of the monitors require some cleaning, don't they, and some regular maintenance to keep them working well. But I think because we, particularly as our iron is assessed on our spot samples, OSM spot samples, you don't get an average on those, so a couple of fails, your site's failed. So in terms of relative risk for those sites, I think as a company we're tending to like the iron monitors a little more now, getting used to and working on trying to improve them a little bit more to be as reliable as they can be. And particularly if the effluent's of good quality, your monitor runs really well, doesn't it? But if it's getting a little bit more turbid, it does tend to go, the monitors get a little bit affected. So I still want to keep turbidity and iron, and rely on them more and allow our ops to do other activities, a bit less on-site testing and rely on the monitors some more. I might be in the minority around that within the operational teams because they do like to double check that it's just right. But yeah, we've got all these systems, we should be using them more, shouldn't we, for monitoring? Yeah.
Thanks, Ryan.
Narinder.
I'm sort of wondering, it's Narinder Sunna from Stantec. I'm just wondering if the first site, I forget what site it was, did you consider any other options? Because it looked as if the site itself was, you know, very broken. So wondering if you sort of considered, just, you know, T-Tech there sponsoring the you know, this particular element. Did you consider fantastic technologies like their process or oxidation ditches, etc.?
Yeah, and other processes were considered for Booton. Booton's been a difficult site over a number of years, and we've applied various not as successful like solutions to that site. So yeah, they were considered within the optioneering side of things, putting a ditch in or other, you know, other technologies. But the filters, thinking about assets that are still in good nick, that have still got a good life in them still very good. We just need to make them more mineral media and add a bit of extra protection for the ammonia change. So yeah, there would have been, I wasn't privy to all the details back then, but there would have been some really good cost-based decisions, and I'm sure a fair few arguments around what's the right answer for Booton. In my previous incarnation as process scientist, I've spent too much time there, and it's one of those sites that was a really important one to get as good as we could, just to support our operational teams and get confidence in what we were going to do. So, yeah, lots of options considered, of course, as all with optioneering, but it seems to be pretty good. We're happy with what we've got, but yeah, we would have considered alternatives as well and costed them. So, I hope that answers your question a little bit.
Yeah, it's just you had a very complicated commissioning as well. So, yeah. Would you? Okay, so let's ask him. Would you have made the same decision?
In my happy world, I'd have built it in the field next door, brand new, and commissioned it offline. That would have been a really good thing. Yeah.
Thank you, Narinder. Excellent question, obviously. A T-site would have been marvellous there. Yes. Unfortunately, I was working for Veolia there. There's a very good MBBR at Booton.
Yeah. Don't want to bring you in on that one, but yeah.
But next time, Rowan, that'd be great.
Time.
Hi, Mike Jordan from Royal Haskonian. I just wonder if you can comment about the additional sludge production from the chemical dosing. Has that increased tanker movements? How has it affected your digestion sites? And how did you work that into the whole life sort of carbon costing of the solutions?
With each of the solutions, there'll of course be REOC considerations for additional tankering away to other sites. We've already got a lot of sites that do iron dosing anyway, that are taking sludge to digestion sites. So that's not a major change for Severn Trent in that way. What I mentioned particularly was Harvey about additional sludge load. With the chemical dosing, it didn't half pull a lot of sludge out from the trade waste side that became quite a challenge, and it's quite a difficult site to get to as well for the tankers. So in practical terms for that site, it really was a real push. We really must get this site free of sludge to allow us to dose effectively. It was one of those sites where it was really quite tricky. But yeah, on our other sites, that does go into the business planning for the sludge tankering programs, and also the digester refurbishment, and we're moving more to THP as well on digesters. So again, capacity being increased across the board. So yeah, it all comes into the big program. But yeah, sludge is always an interesting one, and there's always a push on budgets, isn't there? Just one more tanker to get it out. It's great. Thank you.
That's great. Thank you, Rowan. We'll let you go. We'll release you this time.
Thanks.
So just final logistics, as I mentioned, drinks reception in the exhibition area, 5 o'clock. The start tomorrow morning is 9 o'clock in room 1 for the plenary session. There still is a presentation until 5 o'clock next door, so you can either sneak into there quietly or move to the exhibition area. Thank you very much, and thank you to all the speakers for being on time this afternoon.